Okay, so I'm assuming that most of you attended the webinar that we had. I'm going to turn off the timings. I don't think, yeah, I got to turn off timing. I think most of you did attend the webinar that was given, but we're going to go through a lot of the material slowly and carefully today to make sure that you have all the information you need about the technology and how to design with it, so that when you go off and try to make your own designs, that you have what you need. And one of the things I talked about with Priya yesterday is maybe we'll go around the room and later, after we're finished with the material, and try to understand what you'd like to do, what you'd like to achieve, what kind of chips you want to design, so that if there's additional material that you'd like to have, we can supply it to you. So the first thing we want to do is we want to review the technology. So I'll go over the fabrication process and how the devices are made, so you can really get a good feeling for it, and then explain the mask layers that are used in L-Edit. So you can see the connection, between the masks that we're drawing in L-Edit and how they're used in the fabrication process. And the other thing we'll talk a little bit about is additional layers that we use in the layout tool that don't really have a lot to do with the fabrication process, but we need them for the purposes of checking your design and making sure that your design is correct. So that's something that we didn't have a chance to talk about yesterday, but we'll discuss it today. So as before, if you have any questions, let us know. So this first part is I'm going to run through the fabrication process of the JFETs. And up in the upper left is shown a schematic of what the different materials are and their colors. So as we go through the fabrication process step by step, you'll understand what color you're looking at. So the first step is just to start with a silicon wafer. And so it's 420 microns thick. And the resistivity of the wafer is given there. So if you do need to do any calculations, you have that number on the resistivity of the substrate. And then after that, there's an epi layer. It's called an epitaxial layer that's placed, which is the green. It's called SiP. So silicon P-type epitaxial layer. And so that's doped with boron. And that is in contrast to the wafer, which is pretty thick. So these are cartoons. The thicknesses are not shown to scale. So, get that really thick substrate wafer, but the epi layer is only 1.6 microns. And you'll notice that, there is a plus or minus 10% there. So all of these steps have some variation in things like the thicknesses and the resistivities. So, for example, the wafer itself could vary by as much as 25 microns. So, it could be 395 microns. So all of this is important to be thinking about. I think you're going to hear from Abbas later about COMSOL simulations. And if you do any simulations, some of these material properties do have variations. And that's important for simulation. So after the epi layer is put down, then we have some alignment markers that are defined. And so what that means is this mask called align is used to put some marks on the periphery of the wafer, so that other steps can be aligned properly. The masks for the other steps can be aligned properly on top of the material that's already deposited. Now, just something for you to remember, you do not have to design the align mask. That align mask will be created either by the CMC or by the 3IT. So you will not see the mask called align being put in your design kit, because these marks will go at the wafer level. You will be designing an individual die on the wafer, but the alignment marks will not be designed by you, and they'll be put on after all the designs are put together on the wafer level mask. And so we won't show these in the diagrams, but they're typically on the ends of the wafer, or around the outside. Okay, so again, we have our alignment. Again, if there's something not clear in the fabrication process, give me a shout. So then we do some silicon dioxide deposition with PECVD. And this is very thin. It's 300 nanometers. So you can see that's that blue color there that's on top of the SiP. And then what happens after that is some photoresist, which is this red color, is deposited, and it is etched by it's developed using the implant mask that you will draw, and that photoresist gets developed, and then the SiO2 is etched through that resist mask. And so that's going to form the implanted regions of the devices. And so then in step 6, there's a boron ion implantation that occurs, and that occurs everywhere on the wafer, but it's blocked by the by the photoresist, so that ion implantation only creates implanted regions where we're going to have the implant, where you draw the implant mask. And so that's the implanted regions, which will be part of the JFET. And then on the back side, in step 7, we're going to have a phosphorus backside ion implantation, so that when the backside contact is added, there will be a layer of phosphorus ions between it and the silicon. All right, then in step 8, typically there's an annealing step. Whenever you do an implant, there's usually a temperature step that occurs that moves the ions into place for after an implant. So annealing is usually a temperature step. So it doesn't have any masks or anything. It's just the photoresist is removed, and there's a temperature sweep, so the ions are moved into place. And then in step 9, excuse me, we have the yellow material, or I guess I should say gold material, which gets deposited on the backside. So that's a backside metallization, which is titanium, which is 200 nanometers, and then aluminum, which is 500 nanometers, that gets deposited on the backside for a backside contact. So that's that kind of orangey color. Then we go back to the front side, which on this one, the front side metallization uses chrome, 20 nanometers of chrome, and then gold. So on the back side, it's titanium aluminum, but on the front side, it's chrome gold. So here, that's a yellow color. So the front side metallization is different than the back side metallization. So here we have chrome chrome gold, and the gold, as you can see, is 500 nanometers, and that's deposited and etched using a liftoff process. So here, this is a mask that you will design, and that's the metal mask that we'll see later in Edit. So that's that yellow material that was it's deposited everywhere, and then lifted off in the regions where the metal mask is not present. So from there, now that's where we have those the metal above your implanted regions. So now in step 11, we do a PE CVD of 500 nanometers of a silicon nitride deposition. And that's in contrast to the SiO2. So here the passivation layer is a silicon nitride. So that's that kind of lighter blue color that is covering all the way on top of the chrome gold connections there, the metal. So we have that passivation layer everywhere. And then a photoresist is spun on again and developed using the via pad mask. So actually, this mask, I wanted to be clear about that, is that when you draw in Edit, you're going to be drawing two separate via masks, and those via masks are going to be combined so that actually in step 12, both the pads, that are above the openings in the Si silicon nitride above the implanted regions will be etched, and the regions over by where you're going to have probe pads, they'll be etched too. So there's a single step. So if you go through this fabrication process, you might get confused and say, hey, I only see an etch using via pad, but there's actually a via mask, which is the combination of the via gate and the via pad. So what you're seeing here in this etch is actually, above those little implanted regions. It's one thing, and this one, I think they're showing the via pad mask over to the right. So you can see it's etching where there isn't an implant. So that's using the via pad mask. But there's also another etch where there's openings using the via gate. Okay, so here we go, and we now have a wet etch of the SiO2. So because those openings are created, so there's both the etch of the silicon nitride and the etch of the SiO2. So now we have those openings present. So what's not shown is the use of the via gate mask. So that's another step. And so the layers that we are using that are being utilized during the fabrication process are shown here in the mask layer table. And so let's go over those layers and make sure they're very clear for you, so you know what you have to design. So the first step that you saw in the fabrication process, it called out something called the implant mask. So that was where the ions are going to be implanted, and that is going to be in GDS number 1. So you draw when this is written in this fabrication. This is written. The digitized data equals dark, and so that means you draw the mask where you would like to have the implanted region. And so, in these diagrams, you can kind of see what's going on, that, we will be making contact to the Edit. So whenever there is, the area inside the polygons, since the tone is dark, the step will be applied to the area inside the polygons. And then the area outside the polygons, the material, in the one case will be etched away. And in the other case, if it's a hole, like the vias, the material will be, retained. So we actually have two different kinds of masks, as we talked about yesterday. The implant and the metal, you draw where you want the material to remain. And then in the via pad and the via gate, you draw where you want it to be removed. So that's very important to remember when we look at these structures. And so the data that gets put on the mask and gets sent out to GDS2 is the area inside of the polygons. And this may seem reasonably obvious and you know, very clear because we tried to make it simple, but you know, there are other possibilities. And so sometimes, you know, the masks that get drawn, they invert the polarity. And as I talked about before, you know, you can have various combinations, but this one is done in a very logical and reasonable way for what we're trying to achieve. Then I'm going to move on to the next slide. So this is how now we're going to go from the masks that are being used in the fabrication process to the masks that you draw in LEdit. And so this table is going to give you an understanding of those masks and what color they are in LEdit, and you know, how you will draw them. So let's look at the first one. First, you'll notice that there is a layer called substrate, but that is not referred to in the fabrication process. That's because there is no need for a substrate mask in the fabrication process, because what you're doing in the fabrication is you're applying it to the whole wafer. But the substrate here in our in LEdit, we have to draw that because the CMC is going to limit you to a certain size for your die. So the die, they want to make sure that when you draw your design, that it doesn't exceed a certain size. So they're going to give you a mask layer that allows you to draw the outline of your die, even though, you know, this mask is not needed for fabrication. It's just a way to check and make sure that your design, all the polygons that you design, fit within an area that is assigned to you. And so we'll look at that a little bit later. And you know, that's one of the things that's specified by the CMC for this run, is how big of a design they're going to allow you to submit. And as far as I understand it, you are allowed to have either the maximum size, or you could have it smaller. So Priya, are you going to have like exact multiples, or they can draw any size as long as it's less than the minimum?
So either we can have a 10 mm by 10 mm or a 10 by 5. I'm sorry, 5 by 5.
Okay. So the idea here is that you will be able to have either a 5 by 5 you know, a size of your die, or a 10 by 10. And that substrate layer is going to be used as an outline for you in your design to make sure that, you know, you don't by accident draw some geometry outside of the area, you know, where it should be, right? So that mask is not going to be printed on the wafer, of course. Now, so we call that the design area boundary. And the color, just so that you know, it doesn't interfere with the drawing of everything else, is going to be shown in outline only. So it's going to be a big black rectangle that will allow you to make sure you keep all of your design within it. And when we look at some designs, which we'll do after the break, you will see that, you know, where that substrate looks, you know, where it's placed and how it looks. And so the next mask, which is called the implant mask, is a yellow mask. And so that's GDS number 1. And that's the implant mask that we saw before. And its color is yellow. And you can see I've shown a little snippet of a design here. So can you see where I point with my cursor, Priya?
Yes.
Okay, great. So you can see this yellow mask is around the outside of this other polygon. So you can see this polygon is sitting on top of the yellow mask. But if you did a hide layer, you would see that this is all one yellow region, which is your implantation mask. Then, so typically, we would then use the other mask, which is called the metal mask, that will be going on top, which is the green mask. So anything you see in green is metal. And that should probably just say topside metal, not contact. So we'll correct that. That should, so this green mask metal GDS number 2 is the is green. So you can see here, here is a pad pad cell which has metal around it, and it has in the center a via pad which is blue. So you can see here, this is a blue square within a green square. And so this is where your hide and show of layers is going to be very helpful. When we look at the designs, we'll look at them layer by layer, but you can see the colors kind of interact. If we turned off the green mask, you could see that this is a bright blue square, and that's the via pad. And then we also have now the last mask is called via gate, and that is the openings in the passivation for the gates of the JFET, and those are red. So we've got 5. We have 5 GDS numbers here. And we have 5 different layers, and the substrate, as I said, will not be digitized onto the wafer. It's just a layer for you to use that indicates the outline of your design. So you don't really even have to assign it a GDS number because it's not going to be printed. But for being able to exchange designs, it's helpful to have that. Now, are there any questions about the masks and how they're used in the design? So the thing I wanted to point out is this red, both the red and the blue here are both openings in the passivation layer, and they are used at the same time in the fabrication process. They just are shown differently because they have different design rules. So when you're making a gate, there's rules about how big the openings in the passivation can be, and when you're making a pad or a connection to the metal, the openings have to follow different rules. Okay, because in the one case we're working with a transistor, and in the other case we're trying to make a contact to the metal so that we can talk to the outside world. So any questions about that? Are we clear on the masks? Yeah, okay. All right, I'm going to assume that's a big yes. So we're going to talk about what's in the design kit for a few minutes. And then we are going to have a guest presenter who's going to tell you about some of the simulations that were done in COMSOL of the JFETs. So I'm going to talk to you a little bit for about 10 minutes on the design kit, and then we will have our guest speaker. So what's in the design kit? How do we help you design these structures? So in the design kit, as we talked about, we have to define the grids and the technology. So, we encourage you to use the same grids that in your design that are in the design kit. Sometimes there may be reasons why you have a different grid, but you may want to start out with the same grid. The layers are set up for you. All the GDS numbers and everything that's ready for the fab is set up in the design kit. all the design rules are in there. We looked at design rules yesterday, so we will go over the design rules in great detail, and you'll actually run the design rule checker. And we also have a reference design, a design that has been worked out for you so you can see what a proper design looks like. We'll be looking at that reference design in the afternoon. And then also in the design kit are useful cells that you can grab, like pad cells are helpful so that you don't have to design things. And the reason why we put these in there is that they're already correct and that you can just grab them and use them. And yesterday we talked about programmable cells. So we will actually show you the programmable cells that were put in the design kit so that you can, you can use them in your design. You don't have to use them. You can draw the mask objects directly yourself. But the thing that's nice about these programmable cells is they're already design rule correct. So they should work out of the box. So if you want to follow me, you can open the design kit. I have provided in the Dropbox. There is there's a file that is the design kit, and you will be able to follow along with me if you want. Otherwise, these slides are going to be given to you, and you are, you'll be able to take a look at what I've done or what we're doing, when you, I guess you are home since everything is virtual, but you'll be able to go through these slides again with the files that are there. So, but I'm going to go ahead and open that file for you. And we'll take a look at what's in there in the design kit. Okay. So I'm bringing up my edit, and I'm going to do a file open because I'm actually going to open the design kit. Now, something we didn't talk about yesterday is that if you have, once you open a bunch of files, edit keeps a recently used file list for you at the bottom, and you can control how many items are in there. So I'm just going to go ahead and go to my pre-assigned files, and we grab the most recently used file because I was playing around with the design kit. And the design kit is open to a cell that has the design in it. So if we go to first, let's go back to the slides. I've opened that design kit, and you actually have it in the Dropbox. And let's see here, let's go here. We are going to go to setup design and take a look at the grid that is being used in this design kit. So if we go to setup design, you will see the technology name. And before yesterday, when we were using the technology from the MUMPS process, it said MUMPS version 11 when we were looking at, I think we looked at the RF technology that was for an RF switch. And in this case, you'll be able to see which version of the design kit is being used and what this is for. And so that's something important. Was asked yesterday, well, how do I know, that I'm working with the design kit? So this is the way to tell, and you can see which version. So Priya has said that this is version of the PDK version 3 alpha. And we put on the a little underscore class here because we're using this example. This is an example of the PDK for the class, but we will be sending you the quote official design kit, or Priya will, the official design kit. So we have underscore class here because we've, this is not the final version. It's just the version that we're using for this class. Okay. And here you can see the technology units are set to microns. Okay, we're kind of used to that. The database resolution is set to 1/1000 microns. So we're kind of used to that. That's a nanometer. So now let's go to the grid tab. And you can see here that the major displayed grid is 10 microns. The minor displayed grid is 1 micron. And yesterday when we were talking, and you can see here, when I opened this design, you can't see the grid yet. So this is something that I'll point out today, is that it says it's going to suppress the grid or not show it if it would be less than 20 pixels. So that's why when you zoom in, you can see your dots, and when you zoom out, you can't. So this setting shows you when it's going to start suppressing the grid. The other thing that's been done here is the mouse grid is set to snapping, which is good for beginning, as I said. So you will have a snapping cursor, so it's going to snap to 0.5 micron. And as we talked about yesterday, the reason why we wanted to go with 1/2, even though most of the design rules are on 1, is that if you do any sort of routing, as we talked about, the center line of the wire will be on a grid point. But if, say, the wire is 5 microns, you're going to have 2.5 microns on one side, 2.5 microns on the other side. So you're going to have to address 0.5 micron. So that's why the mouse snap grid is set to 0.5 micron. And then the other big change from what we looked at yesterday is the manufacturing grid is being set to 1 micron. So that's different than the manufacturing grid that we saw. Polymers was 0.5 micron. And as we will talk about today, further on in the class, you will see that the manufacturing grid being 1 micron will have consequences for how we do the design rule check, how we represent all angle wires, and other types of curves and things like that. So we'll talk about that later on. So just to answer the question of the person that says, what is an all angle design? You'll see here, these areas here, the ones that have a lot of red in them, those are the JFETs. And they are done using they are all what we call Manhattan geometry. They're squares, rectangles, things like that. But you can see the routing wires for convenience. Priya has done them at an angle because it was easier for her to fit in the routing. She could have, come out and routed straight and then across in a what we call Manhattan fashion, but she chose to go ahead and put them at an angle. So that means that her design has all angles in there, and we'll talk about what that means for you. So where we are now is excuse me. We opened the design kit and talked a little bit about the grids, and now and we kind of reviewed the technology. So we are ready to have our guest speaker is going to come in and talk about some of the simulations of these structures. And then we'll continue on looking at the design kit. We'll do some design rule checking. We'll look at some designs. We'll talk about best practices in the rest of the class.
So today we have with us Abbas from York University. He designed his using the JFET technology in the previous run. And complementary to that, he has also developed COMSOL models, which will be available to all of you as part of the kit that goes along with the ESP. So now in this session, we are going to understand how to run these COMSOL models and all the other details associated with that. So Abbas, if you could introduce a little bit about yourself, about your lab, and then start with this.
Yes, of course. Hello, everyone. Thanks for joining me actually in this talk. My name is Abbas Panahi from York University, and I'm from Department of Electrical Engineering and Computer Science at Lausanne School of Engineering at York University. Actually, in BIOS, we are focusing on developing biosensors and microfluidics for different applications. And in my PhD, I'm focusing on developing JFET sensor and its integration with microfluidics for biosensing applications. Currently, I'm a MyTech Accelerate intern at CMC. And in this collaboration, we are working on JFET and its design and microfluidic fixture and its simulation studies toward using that for cell analysis and actually for high throughput cell analysis for infectious diseases. As a part of in a part of my study, I actually started using COMSOL multiphysics for simulation and modeling of JFET. And actually, I'm the initial purpose of my study and using COMSOL multiphysics was to designing a platform for actually modeling the open gate JFET before fabrication, because when you do your layout design, definitely you need to understand the sensor response and the sensor output, and in better words, the transfer characteristics of the sensor. And by having that, you can have a more robust design, and actually you can start designing your circuit and your fixture design, and in parallel with your layout design. So actually, this platform helps you to do a parametric design on open gate JFET, and start other components, other readout component design, early on and before fabrication. This is COMSOL application version of the COMSOL model, and we will actually let you have the complete COMSOL model very soon. And this application helps you to do a complete parametric design, and you can get everything you need for in terms of electronic characteristics of the sensor. So it's actually very good for the initial design and initial guess of the sensor response. In this application, you need actually, first of all, I would like to talk a little bit about the structure of the sensor. As you can see, I have put the structure of the sensor here to actually look at the structure and change the size and different parameter. It's more easier. And as you can see, we are facing a PN junction and a P-type layer and an N-type layer. And the main channel is P-type, and the supporting channel is N-type, as you can see. And we have source and drain and minimum surround around the source and drain, and we have implantation doping under source and drain, and we have a specific thickness for a P-type and a thickness for N-type, and Of course, we have backgate for controlling the channel conductance. The most important parameters that you need to consider for the design, and basically you are controlling them through your layout design. Those are the LS, LD, LMS, and LO, which LS and LD defines the source and drain lengths, and the LO defines this open gate lengths. And LMS, we have two LMS because they are the same. Of course, you can choose them different, but this console model has been designed based on this assumption that these two values are same and symmetrical. So you need to, these are the values that you choose in your LED design, and then you can come here and put those values in these boxes, and then click on compute and get the IV curves and hole concentration, electron concentration, and then do your specific design. So first of all, the most important design parameter is open gate length, because here is the sensing area of the sensor, and after that you need to define the source and drain lengths, and you actually design the source and drain position in your LED, but here you physically actually simulate that sensor. So actually, after choosing the open gate lengths, you need to choose the source and drain, and after that you need to define the LMS. But the way that you put numbers here is in this way. First of all, you need to choose the open gate lengths, and then source and drain. And so, for example, if you choose 5 as open gate, and then you choose 20 as source and 20 as drain lengths, and after that you need to put the summation of all of these values in this box. Total length means the total length from source to drain. And in this part, actually, you need to consider the LMS yourself. You can choose LMS here, and you need to add LMS to the to the sum of other open gate and source widths and drain widths box, and put the total length here. So by these and after that you need to define the p-type thickness and n-type thickness. Something that is very important. I don't know, Priya, if the fabrication can control or change the p-type thickness or n-type thickness, but I have designed the platform in a way that you can choose those values as well. I'm not sure.
No, as of now, because we are getting a wafer which already has that epi layer, we don't have control over that.
Okay, but I have actually put those numbers, those boxes as well for parametric design. And so you can actually choose, change these numbers as well to see how these parameters affects the sensor response. And We have another important parameter, which is called implantation depth. And under source and drain, we have implantation, to have the contact. So in that implantation, which is P plus doping, you can define the implantation depths, which I think it's between 0.5 to 1 micrometer. And based on the fabrication information, you can actually define this number, or actually define that as a part of your design to CMC. And these are the geometrical values, geometrical parameters, and then we move to material, doping levels, which we can call them material properties. For example, you can define the P-type doping, the doping levels here in P channel, and then N-type doping, and the doping in N-type layer, and then source implantation doping and drain implantation doping. And so in this area, you can define doping levels in simulation. Okay, so until now, you have already defined all parameters, and everything is okay. Now we need to define the voltage and the biasing conditions. Something that is very important to know about the JFET working principle is that this is a PN junction, and when you apply voltage from backgate and you have a voltage applied on the drain, you need to make sure that this PN junction never turn on. You need to make sure you never turn on this PN junction, because if you operate the sensor in a way that you turn on this PN junction, you will get some leakage current from backgate. So that's a source of error, and that will affect the sensing performance of charges and solutions and biomaterials in open gate area. So we can operate the sensor in two mode, forward bias and actually reverse bias. And in reverse bias, it is safe mode to operate, use this sensor. And in reverse bias, you need to apply negative voltage to the P-type, to the P channel, and positive voltage to the backgate. So for that reason, I have only considered the reverse bias mode here, and actually in these green boxes, you can consider the minimum and maximum values for the range of voltages, and and then click on compute to do the simulation. So please be reminded that you need to apply minus voltages for drain and positive voltages for backgate in order to make the sensor operate in reverse mode. So after computing, after the computation is done, you will get four curves, 4 pictures here, and as you can see, one of them shows the drain source current versus the drain source voltage, as you can see here. And this curve is very important, is the most important transfer characteristic of JFET. So by means of this simulation, and you can get all the electronic characteristics of JFET, and then for example, you can define the sensitivity, the current-based sensitivity with this curve, and you can define the gain. You can calculate all parameters, for example, threshold voltage and other important electronic transport properties for your design, and actually optimize your design in a way. Another important curve is the drain source current versus backgate voltage. Actually, when you want to design a sensor, especially for biosensing, for chemical sensing, you need to have a reference voltage, and the best option here is to use, I think, backgate as your reference voltage to complete your design and, to define and characterize your sensor. And this curve actually enables you to, define sensitivity of your sensor, and by comparing the changing reference voltage, which is the backgate. So basically, you need these two curves, and then you can get the information out of that for sensitivity and other parameters, other electronic parameters. Also, you can get the whole concentration contours, and as you can see, for example, you can zoom in and save the picture, and then use that for your publication or everything, and for your understanding. For example, the effects of you can understand the effects of biasing and effects of voltage on the channel conductance. For example, this is a whole concentration, and we can simply understand that when we apply more voltage, backgate voltage, actually we are closing the channel, the conductive channel. As you can see, we are this is the contour for drain source -10 and backgate voltage equal 1 volt. And as you can see, actually this is the condition for the yellow one, the yellow line here, and we can see that the sensor is very, very close to be pinched off. So yeah, you can use these diagrams for your understanding, and if you want to, for example, do mathematical modeling of this sensor, actually you can use these contours in order to estimate the mathematical functions and other important parameters that you can get from these contours. So it depends on your application, but the most important output values that you need, I've tried to put them in this application, and yeah, I think and yeah, I'm done, Priya.
Do you want to simulate and show once?
Actually, it takes, I don't know, let me, for example, let me compute, for example, if I change it to 10, and consider the source widths and drain widths 2020. And then I need to change the total length because I have added 5 micrometer to this one. I need to change it to 660. And then, for example, other parameters, for example, change this
Is
one.
there any way to add, like, control the mesh from here?
Oh no, actually we can't control the mesh from here. And you know, I didn't know this parameter is important to put it here. And you know, I have you know, meshed the sensor, but we can add that. Of course, we can add that. I think because meshing here can be you know, we can reach to a very efficient meshing method, and then, you know, use that for every simulation. But I think that's important, and, you know, I didn't consider that meshing here in this application.
Yeah, if it's possible to add that, like if somebody wants to see a quick run by changing something, or if they want to go more in detail and do a complete meshing. So if we could allow that.
Yeah, sure. Actually, by so we changed some values here and then click on compute. And as you can see, the application is running, and I think it takes some minutes.
Yeah, meanwhile, we can check if somebody has any questions.
Yeah.
We were talking about the design kit. So now we are going to talk about the layers that are present in the design kit. So I am going to, let's see, I have to move this so I can't get to everything because of the, let's see, maybe this will work. Yeah, because of the, I have to try to move the LinkedIn, this sharing thing. Okay, there we go. Now I can get to slideshow. Okay. Okay, so now we're going to look at the layers that are in Edit that we talked about that make up the design. So I will go ahead and do this live with you, and you're welcome to follow along if you want, because I provided you with a version of the design kit that's there in the class. So we're going to go into set up layers, and we're going to review the layers, and let's go ahead and do that right now. So let me bring up Edit. Hope those people from the East Coast had a nice lunch. We all had a probably nice breakfast on the West Coast. Okay, so I am opening the design kit that I provided you in the Dropbox. Let's see if I can move this somewhere. Okay, let's see if we can move our Edit down. Okay, so now we are going to go into setup, and we're going to go into layers. And can you guys see my screen okay, Priya?
Yes.
Perfect. Okay, great. So as I talked about that, we had a layer called substrate boundary. And that is just the boundary of your design. And you can see that we've set it to GDS number 0. And the rendering is set here. We've got no fill pattern, and it's going to be a black outline. Then we have the implant over here, and that is GDS number 1. And it is kind of a goldish color when you draw it in Edit. These layers are set in the design kit to correspond to the documentation. So we prefer that you don't change, as we talked about, that you're going to get all of this technology information from the design kit. So we would like you to keep the colors the same as in the design kit. So please don't change them, because the reason why we want to do that is that when the CMC looks at your design, maybe they're helping you or something like that, or 3IT, if everyone uses the same colors, it's easier to recognize the structures really quickly. So that's why we have, all agreed on a set of colors. As you know, the colors are arbitrary. We could have made implant purple, but we all had to kind of agree on the colors, and we're doing that just so that student A and student B don't use different colors. So, looking at them, we'd have to say, okay, well, what color is your implant? Blah, blah, blah. So let's just all use the same colors, and life will be good. Then we also have the metal layer, and we talked about that. That's GDS number 2 over here. As we also talked about yesterday, we talked about wires, right? So we have set the width of the wire to be 5 microns. And that is because the minimum shape that you can draw on the metal layer is 5 microns. So that's why we've set the default for the wire settings to be 5 microns, so that if you just start drawing wires in metal, it'll automatically be 5 microns. And later, when we look at the design and we are, playing around with the design, we'll remind you how you can set those wire widths to be something else. There's no harm in making them wider. That reduces their resistance and the total resistance of the wire. But if you are going to you're just trying to route your signal from A to B, then you have to at least make them 5 microns so that they will pass the DRC check. Okay. So you could also, we have set the implant wire. Also, you could draw your implants with a wire. Typically, we use wire for routing, but sometimes people find it convenient just to draw, boxes with wires. We recommend the practice of using wires just for routing, easier to be able to connect to other structures if we do that, but that's kind of up to you. Then we also have a layer called ViaPad, that's GDS number 3, and the rendering of that is a blue color. You can see here, and then the last layer is called ViaGate, that's GDS number 5. And it was intentional. There is no layer with GDS number 4, because I think that initially in defining this design kit, there probably were 5 layers, but sometimes, as the collaboration between fabricator and PDK maker, you add or subtract different layers. So we do have 1, 2, 3, and 5. Is that correct, Priya? Maybe you guys had an extra layer previously?
So we have layer 4, but that is only limited to 3IT to make changes. So
right. Okay. So we're not, yeah. So they're yeah. So as we talked about that, we use they use a layer called align for the alignment marks. So they will draw that, or probably or maybe CMC will draw it, so you don't have to worry about it. And then GDS number 4, as Priya explained, is used by 3IT. So we're giving you access to 0, 1, 2, 3, and 5. Okay. Now the next layers in LEdit are these are the layers that LEdit uses itself. So for example, the grid layer here, this is the layer with which you use to draw the little dots that become your grid. And then these other layers here are also used by LEdits for different purposes. Like when we did the DRC, you notice that we had a layer on which the DRC results showed up. And when we zoomed to the error, it showed up on the error layer. So there's some layers that L-Edit uses for its internal purposes, the drag box when you make a little drag to zoom, the origin layer when we draw that little cross that you saw that represents the origin, the cell outline layer, which is the outline of a cell. You know now that cells have outlines, so that when you see them appear inside, when one cell's inside another cell, it's drawn with the cell outline layer. We also can have what's called an icon layer. You can draw little pictures. And we also have this error layer. Was there a question? I see something showing up in the chat. Okay, maybe that's something else. Okay. All right, I'm gonna let you, if you don't mind, Priya, if you can watch the chat, I'll not watch it.
Sure,
Okay.
I will.
Okay, great. All right, so we talked about these layers, and then finally we have a layer called subshrink. And this is a layer that is used for doing design rule checking. So in fairly complicated processes, we also have layers that are used for design rule checking. So you don't draw them. The design rule checker uses them for checking some of the rules. So we will be talking about this layer later when we look at the design rules and how they're implemented. And the reason why you have to care about this is this layer is that before we do a design rule check, you're going to have to make sure that it is properly set up. So we will we'll talk about that when we talk about design rule checking. But in terms of drawing, these are your layers that you get to specify the polygons on these layers. And the other things are, these are L-Edit private layers. And then this is a layer that is going to be used by the design rule checker. So any questions on the layers that L-Edit uses? Okay. Any questions? Because I will move on. Okay. Hopefully these are making sense to you based on what we talked about previously. So I'll go back to the slides now. Okay. So now we're going to look at all the cells and information that's in the design kit. And so I'm going to go through them with you, and so that when you can use these slides for reference later, no pun intended, so that when you are going to do your design, you'll know the purpose of the different types of cells that are in the design kit. And then I'm going to recommend to the CMC that we do a little bit more of documentation of the cells that are available, so that you know which ones you can use and how to use them. So right now we're going to look at it from the design kit side. We're going to look at what's in the design kit, and then we're going to switch and we're going to pretend that we're designers and we're going to use the design kit. So right now we're actually opening the design kit, seeing what's inside of it. And then later we'll open it by reference so that we can use the stuff that's in there. So I'm going to go ahead and now open my design navigator so that we can see what's in there. So right now, when you open, we have saved the view of this design kit. So the reference design is shown, by default, but now we're going to go and turn on the design navigator. So if you remember dusting the cobwebs from your brain, if we go to the view menu, we will find the design navigator over here. And if we have that, if it shows up as another window, and I like to keep my windows all tidy. So I am going to move my, if you move your tabs, I'm showing you things that I didn't have a chance to show you yesterday, just because we had so much to do. So I've now placed my design navigator on the left because I like to have it over there. And I am going to go up to the window, and I'm going to cascade my windows so that I can have them be nice and handy. I could also have tiled my windows, but I just like to move them where I want them. So now we have our design navigator here. And I'm also going to move my toolbars around a little bit so that we have a little bit more space to look at the design navigator. So I also didn't have a chance to show you this too much yesterday, but today I will, because we have a little bit more time. So I'm going to go ahead and do that, and then I'll move this guy up, and that's probably enough space. So now I can go ahead and move my my design navigator. And we also notice here that in my display for the display of the layers, I have chosen to just display my drawing layers over here. And if I had gone up here and said, hey, let's look at all layers, then I would see all the layers. Okay, so sometimes you really need to look and make sure that you see, you know, what you're displaying. I could, you know, there's other choices here, like which ones are being used in my cell. In general, I switch between drawing layers and all layers. So here I'm just, it's convenient for me because I'm going to be designing. So I would, you know, just put up the layers that I'm going to be using for design. But later we'll turn on all the layers because we'll have some things to point out. So now this design navigator gives us a list of all the cells that are in the design kit. And so there's quite a lot in here. So we're going to go through them with, you know, in terms of groupings of types of cells and what their purpose is used for. So let's go back to the slides. Okay, so now we have opened up our reference design and looked at the design navigator. So the first thing I wanted to show you is the pad cells. Okay, so if we go back to edit here, you'll see that there are certain pads that are part of this design. So when you are doing your own design, you could get yourself a frame and either make an array of pads, or you can put your pads down one by one. You will, you know, you'll be able to use these pads, and so their names are indicative of their size. So, for example, if I double click on the pad 100, you'll see that this is a design rule correct pad that has metal on the outside and the via on the inside. And so the pad _100 via Priya, Priya, can you comment? I think the 100, oh, okay, so the 100 refers to the size of the cell, the metal part, right? And the so this is an 80 by 80 opening on a 100 piece of metal. Is that right?
Yes.
Okay, so maybe, you know, depending upon your probing and things like that, you know, the opening will be 80 by 80, but the metal is 100 by 100. Okay. So you should be aware of that. Take a look at the cells, see what makes sense. Let's see what they did with this one. Okay. So this is a via pad. In this via cell, the actual opening is a 10 by 10. So one of the things we may want to do, Priya, is make this more consistent, right? So we'll have the 100 pad have 100 by 100 opening, do you think?
Yeah, I think that's better.
Right. Okay. So as we said, this is an alpha version of the design kit. So we'll be doing some documentation and showing you specifically what's going on with these cells. So the bottom line here is you have some pads that you'll be able to use. And if we take a look at Priya's reference design here, let's see if I can zoom. Let's see, maybe I'll just use a plus key. Did you use your pad cells in there? Right. So she has instanced into her design 100 micron pad cell there. So she's using the pad cell from her from the library to be able to, from the design kit library, to be able to just draw a bunch of pads rather quickly, right? So instead of having to go and make 2 polygons every time, she has just utilized the pad cells from the library. Okay. All right. So any questions about that? So that was the pad cells. And now we're going to talk about some other cells that are also present. And I'm going to call these the frame cells, because these are cells that will help you create your design, and they've already been kind of set up to be a certain size. So let's go take a look at those. Okay, so for example, here is a cell called My Design 10 by 10. And if we instance that, we will see, and again, we're gonna have to zoom in here. This cell has a polygon, as you can see, of a substrate boundary here. So it's got a box which has a boundary polygon that makes sure that the design is in a 10,000 by 10,000 micron square. And then inside this frame, pads have been placed on a regular grid for you. So you can see here, you can make use of this cell, and it has a bunch of instances of the pad 100 cell inside of it. So this is a frame that you can use. You can put your design inside here and utilize it for your purposes. Question?
So I was going to mention that next. So you don't have to stick to those pad sizes. So first of all, these are pretty small. So you would, if you were to go with this fabrication route, you would only be able to wire bond to them. So you could design your pad sizes much, much larger if you want to make a different type of connection. So there's no restriction. This is just one kind of standard that we have that we've already inbuilt as a reference for you. So you could change that and go with much bigger sizes.
Right, and we're going to talk about that when we talk about later on in the class, once we've kind of been through everything, we're going to talk about some recommendations that we have on pad placement, pad type, and also some previous experience, because we've had 2 designers that were part of the webinar, and they talked about what worked, what didn't. And one of the things that they called out was, you know, the fact that pad placement is really important for some of their biological experiments. And so, you know, we'll both talk about some design suggestions, and then we will later on today, we'll talk about, you know, maybe go around the room and talk about what you guys want to do with this design kit and see if we can provide even more helpful information. Okay, so a lot of stuff in the pad. So one of the questions that's in the chat here, I do want to make this clear, okay, and about the design kit, right? So we're going to actually talk about this a bit later, but if you use the cells, if you instance the cell from the design kit, you can't change it. So if you want to, say, use the Priya's 10 by 10 and change it, then you're going to want to copy it, because if you make a copy of it, then you can move things around. So Priya's question is, you can place them wherever you like, is correct. You know, you can put pads anywhere you want, but if you use a cell from the design kit, you either have to use it as it is, if we do an instance, Or if you copy or reference, and if you want to make a copy of it, then you can move the pads around or use different pads. I'll show you how to replace parts of the instances. There's very efficient ways to do that. And so we'll look at both methods later on when we actually start doing our designs. And I'll show you what that all means. But in general, if you use the individual pad cells here, you can just plop them down using the instance command. If you use the frame, if you start with her frame here, then you would have to either use it just the way it is. Let's open the frame cell. Sorry. Yeah, if you instance this, you wouldn't be able to, you wouldn't be able to easily change it because it's a library cell. But if you copy it, you'll be able to change it. Okay, does that clarify the question?
Yes.
Okay, so just so you're clear on that too, Priya.
Yeah.
Okay, great. And we'll talk about that a little bit later. And one of the things that we didn't have a lot of time to talk about is I'm going to show you how to go inside, once you're inside of an instance or you have some cells, we'll do some more work on cells so that, they are more clear for you about what you can do and what you can't. And also the, what is available in terms of the design kit and which way we can use it. Okay, so let me go back. I was talking about the 10 by 10. Let's look at a few other ones here. Here is a 5 by 5 that they have laid out for you. So, Priya mentioned that the preferred idea here is to have either 10 by 10 or 5 by 5 die sizes, and they will clarify as to whether you could, make something that's even smaller or how that's going to work. Is that right, Priya? You'll give some guidance on that?
Yes, I mean, I could just probably add that comment here. So
Sure.
Usually, because it's an MPW process, everybody designs on a quarter wafer. You could go higher too, but typically on a quarter wafer, if you do a 10 by 10 design, the output as an output, you would get about 10 to 11 dies. But if you were to design a 5 by 5, you would get about 40 to 44 chips. So if somebody wants to have more chips and give it a try, they would go for a 5 by 5 design. But then again, you need to keep in mind that if the die size is too small and you are looking at, making some different kind of connections, it might be very small to handle. So based on your application, you could either choose 10 by 10 or 5 by 5. I think smaller than that would be really, really hard because we basically dice the 10 by 10 to get that. So if you were to make a 5 by 5, it would be populated 4 times within a 10 by 10 die and diced along that.
Okay, so the other question though, Priya, is you are not allowing a 3 by 3 or a 4.5 by 4.5. It's either got to be 10 or 5. Is that correct?
Yes.
Okay, so we should put that in the documentation as well. So yeah, so just so we're clear on that, you can do a 5 by 5 or a 10 by 10. Can you do a 10 by 5?
We can. It's actually, the way it can get diced, right? It could be done if there's a specific reason why somebody wants to go off this thing. But yes, as of now,
all right,
10 by 5 is possible. Yeah.
Yeah, we'll add that to the documentation. But what I think I'm hearing you say is it's a multiple of 5, either 10, 5, whatever, right?
Yes.
Okay, so that's why in the design kit, we have given you a 5 by 5. There's also a 5 by 5 array here. And so there's the, these 5 by 5s, the 10 by 10, and then the reference design that Priya has here is a 5 by 5 size. Is that correct?
That's right.
Right. So that's why her substrate is set that way. So any questions about that? So these are cells that you can utilize in your designs if you want to start out with a frame. And then we also have the reference design, which we talked about. And then there is also a little logo. You can put the CMC logo if you want. And then there's a technology version also on there. So one of the things that you might want to do is, if you're planning to submit to multiple runs, put a little technology version marker on there. And one of the things that this is done in the metal layer so that you can see it. So these are actually polygons written in metal that will then be visible to you on your die, that you'll be able to, pick it up, look at it in the microscope and say, oh yeah, that's the one I fabricated with ESP version 2.1. So that's a little cell that you'll be able to utilize in your design. And the thing that's nice about this particular thing is it's, the polygons are done nicely. Then this is what I was talking to you about, is that this S, for example, this guy here, this is an octagon, 45-degree octagon. So these letters are very nice and will fabricate well. That's important. Whereas this logo from CMC, you can put it on there, but as we'll talk about it later, if you choose to design your own logo and put it on your chip, it probably will not pass design rule check, right? We can fabricate it, but it will definitely screw up the design rule checker. So I'll show you later how to remove the logo and do the design rule check without the logo. Okay. All right. Any question about these cells that we have talked about that are used for your reference?
I have questions about this design example. So I see there are some connections between two different sized paths, but they were not connected to any devices. So what's the purpose of that?
Yeah, okay. So I'll go ahead and pop up the design, but we're gonna have later, we're gonna actually go through the reference design with Priya, because she designed it. And we'll talk about in pretty good detail what's on that reference design. And I believe there's an application note, right, Priya?
Yes.
Okay, so when we get to that part, we will go ahead and talk about great detail about it. But if Priya is willing, I will pop up that reference design, and you can point out what your question is. Let me move this over here, because I think I know what you're talking about. Like, you're asking why this thing is here, or?
Yes, it seems like those are floating wires.
Right. It seems like, where the heck is that going? So Priya, do you want to answer that question?
Yes. So when this reference design was being built, it was also with the application in mind of a printing. So we had one project where we were doing graphene printing. So for the top gate to give connection, what we envisioned was that, you could print the line on the gate and extend the printing to make connection there. So this was done in order to give connection to the top gate.
Right. So when we get to the design, the application, we'll pull up the application note. We'll talk about the design, and you'll be able to see, Priya will describe it a little bit more about what she designed and why it's designed that way. But I thought, okay, if it's on your mind, then let's address it now. But from what I understand, the answer is that there was meant to be a connection made with some sort of printed material. Is that right, Priya?
Yes.
Okay, I see. By the way, do you mind just explaining a little bit more, like when connecting two different sized paths? Is it preferred to use this kind of connection with gradually change the like width or dimension, or we can just use like two consistent with lines with different?
Sure. And again, we'll go ahead and answer this now. We will, as I said, when we get to this part of the class where we go over the reference design, we will talk about this in more detail. And also we're going to have a whole section on good design practices. But again, since it's on your mind, let's answer it now. The bottom line is the design rule, right? So metal is usually, people have been doing metal for years and years. So pretty much, it doesn't matter, right? So if you want to, and I'm going to zoom in here. What Priya's done here is she has her pad, which she grabbed out of the library. So this is the pad cell, and then she's coming in to it. Now, one of the things you want to do is that you want to make sure that, you don't have any little itty bitty, corners over here that are going to cause a design rule check problem. But, she has come in, to it, and then she's tapering off with an all angle. And that is perfectly fine, as long as she has maintained the spacing so that her space from one wire to the next is greater than the design rule, and her width is greater than the allowable metal width. It does not matter if she comes off at an angle or she comes off straight. As we talked about it, we had what we called Manhattan routing, where she could come off straight and then make an angle, a 90-degree angle to come into her JFET, or she chose to just, angle this polygon. I don't even know how she did it, but she chose to do that. So she could have come straight on, and then she would have come in. To this piece here. But you notice if she would have gone, with a 90-degree, she would have then had to move this wire over a bit, because this green stuff would have come over to about here before she made that switch to come in. So, the all angle is more space efficient than the orthogonal routing. But, she could have even, gone in there and, not access the pad, completely. She could have just drawn a wire that was minimum width and come into your pad. The thing that guides you in your choice of thicknesses is resistance, right? So that the design rule around your pad has to be a surround of 10, and but other than that, it's about obeying the design rules, and if you want to have a nice low resistance path, you keep your wires as thick as you can. But from a design rule point of view, you could have used minimum widths of wires. And that being said, if you're with a big production fab that has been doing metal for years and years and years, they don't even care. They don't even blink. It's all, it's something they've done many, many, many times. And that's what they have to do, is make test structures to make sure that the reliability of those connections is good. And so metal is usually not a problem. So it's up to you. If you like, doing all angle geometry, go for it. If you prefer to do some sort of routing where you're on a grid and it's all 90 degrees, you can do that too. The thing that you have to be aware of is that later, design rule checking all angle geometry can sometimes be challenging because of that snap to grid that I talked about. But, it's typically, from a manufacturing point of view, not a big deal. Does that answer your question?
Yeah, exactly. Thank you.
Perfect. Yeah, these are all great questions, and we'll probably, go over this topic a little bit more when we talk more about the reference design. Okay, so let's go back to where we were. Okay, so we were talking about the frame cells, and so we are talking now about those are the cells that you can use to make a frame for your design. So now we're going to talk about another class of cells, which we talked about yesterday, and these are the programmable cells. The cells that I showed you, like the pad cell, Priya designed those in what we call with fixed geometry, right? That's why she had to have a pad 100 by 100 as a different cell than the pad called _10, because in the two cases, they are different geometry and that geometry is fixed. But as we learned yesterday, there's a different type of cell, which is called a programmable cell. And she has created 2 of those for you that enable you to make different JFET structures, a full JFET, and also a gate for the JFET in a parameterized manner. So, and as you remember, these programmable cells are indicated with a little a little icon before their name to remind you. And she's also named the cell _parameterized to remind you that these are parameterized cells. So later, when we actually flip to the design side, we will instance some of these cells just like we did yesterday and have you play around with actually being able to create some of these in your design. But I wanted to point out to you that they are part of the design kit so that you'll be able to use them. And as you remember, when we instance a fixed geometry cell, it just inserts the geometry and the cell outline into your design. But when we instance a programmable cell, what it does is it gives us the, it brings up the interface so that we can enter the parameters that we want for our cell. So in this case, if I instance the gate parameterized cell, which it kind of gives the name up there, it also gives you the parameters that you are going to specify when you are creating this cell. And one of the things we can add to the documentation a little bit is the definition of these parameters, like what does the length mean and what does the width mean on a gate, right? How is that defined? Is it, horizontal, vertical, what have you? So, but you'll be able to see when you play with them, you'll get quite clear on that by using them because they're pretty simple. In fact, Priya, does the length mean the length of the gate and the width is, which dimension is which?
Yes, length should be the channel length. The width means the channel width.
Okay, perfect. Yeah, we'll probably put that in the documentation next version. So we'll go through these in a little bit, but we're looking at right now what's in the design kit, and later we're going to look at how to use the design kit. Okay. So let's go on the next class of cells. So now we're going to get to the design rules, and I will show this on screen so that we can talk about the design rules for this process. So this is, as we know, the design rules come from the fabrication limitations and tolerances that the fab tells us about. And I like to look at design rules, and this is a nice diagram from the fabrication point of view before we look at them from the layout point of view, because you can start to understand where they come from and why they're there, right? So, this diagram will help us to look at some of the design rules. And so let me point out some of them, and then we'll go through them layer by layer. Or mask by mask. So we have design rules come from a physical set of dimensions in 3 dimensions, but they are obeyed or drawn in the layout. So let's cruise around this diagram a little bit and see what we got. So one of the dimensions that is mentioned here is the minimum of 9 microns of this dimension here. And that is actually defining your implant. And if you notice, the arrow is drawn in a very specific way because it doesn't specify the full length of this implant. It's just specifying part of it. And the reason why that is the mask, when the ions are coming down, the mask, the ions kind of go into this part that is not masked off by the photoresist. But when we do the drive-in, the temperature annealing, what will happen is that implant's going to spread out a bit. And, basically you can see why this is being drawn in a circular fashion instead of like a square fashion, because those ions are going to move into place by a certain amount. And even though we're implanting in a 9 micron window, the width of the implant, the actual physical locations of the ions is going to be a little bit different than that. Okay. Now, some of the other dimensions that we see here in this diagram is that there is a space of 2 microns right here from the edge of the metal to the edge of I think this is silicon. Is it silicon nitride that's on the top? I think. No, that may be SiO2. So there's a dimension here that's 2 micron. And then we also we'll see that in the design rule. We'll see 3 microns here, which is the, this dimension here, which has to do with the passivation. We will also see in the pad layer, you can see this is called, it's a pad. So we'll see a minimum of 10 microns that the metal has to extend past the opening in the drain pad. So, unfortunately, this is not drawn to scale because it's really hard to do. So this one is, this 10 microns here is where we get that design rule that we have to surround the pad via by metal. And here we have to surround the metal, by the implant by 2 microns, okay? And then here, this is the 9 microns that we have for our implant. And so there's other design rules that are not shown on this diagram. So we'll probably, add a few more pictures and so you can see, but you can kind of get the idea of where do these design rules come from in how we manufacture the device and why they're there. Because, for example, the design rule on the surround of the hole here in the via is that we want to make sure that we are connecting, that when we drill that via hole, that we hit metal. And if the metal happens to move over a little bit, we could be drilling a hole and not connecting to what we want to connect to. So that's where these process tolerances come from and the design rules come from. Okay. Any questions about this diagram so far? Because now we're going to move out of 3D space and look at layout space. So we kind of have to translate our heads a little bit. Any questions so far? All right, great. So let's move on. So now we're going to go layer by layer through the rules, and then we're going to look at those rules in the design kit, and we will see where they come from and why they're there. Okay, there's some more stuff in the chat. Let's see what's going on. Okay, do we have a lambda for this transistor? Do you mean a rule on, yeah, because the word lambda comes from, you mean the lambda rule for VLSI, right? The size of the transistors, is that what you mean? Yes, okay, great. So in these kind of JFET world, the lambda rules in the transistors, lambda is usually the minimum size that anything can be, and transistors are usually 2 lambda. So in this world, the lambda is set by the via gate. So we'll take a look at that, and there's a minimum of what that design rule will be. And so when we get to that, we'll talk about it. And that sets lambda. So maybe we can also document that a little bit, because lambda is usually coming from the integrated circuit world. So the people, the CMC and the folks from 3IT aren't using that nomenclature. But for sure, lambda, as we see it in the integrated circuit world, is certainly definable in this technology. So we can go ahead and define it for you in the design kit. So you can, for those of you who think about lambda, you'll get it. Yeah, my old advisor Carver, Carver Mead, I guess, really, came up with that, right? Okay, what's in the chat there? Okay, great, super. Yeah, ask me about it when we talk about the gate. All right, so the first one is the implant, and so we talked about that. You could see in the rule, in the cartoon of the cross section, where that minimum width of the implant came from, and then that the implant itself actually bloats out a little bit. So that's why the minimum spacing from implant to implant takes into account the fact that even though you're drawing 9 microns of implant, the actual implant is going to be a bit thicker or wider. And so that's why we have a spacing rule from implant to implant that is something you have to respect. So rule 1.1 and rule 1.2 have to do with the implant. Okay. Why can I, it's funny, every time I interact with the chat, then I can't do my PowerPoint. Let's see. All right, what can I do about that? There we go. Okay, so now let's talk about the metal rules. So the smallest piece of metal you can make is a 5x5. And that's why when we looked at the layer setup, the layer setup had a minimum of, for the wire routing, we had the default of 5 microns. So that when you route in metal, the default wire width will be 5 microns. And that's coming from the minimum width rule that is set here. And then in rule 2.2, the minimum spacing of metal to metal is 15 microns. And so that is important for the routing because as we discussed, when we were looking at that routing and the design, that's why Priya, used those all angle polygons, because she knew that she could only get her metal with, to 15 microns between them. And that's a pretty big space to do. So it's hard to fit all those routing wires in. And that's why she was telling you, that has implications for design die size. Because when we looked at the, when we looked at that 5x5 reference design, the routing took up a lot of space in that design. And so this 15 microns is a big limiter. So that when you're thinking about, do I want a 10x10? Do I want a 5x5? A lot of people focus on, their devices, the JFETs themselves, but you have to think about leaving room for your routing, right? So that's one of the things that, when we talk about the best practices, how do we think about, leaving enough room for our routing in that design? And we'll look at that design quite carefully to see, how we want to do that and if there's better ways to do it. Okay, and then the other rule that we saw in 3D is that we want to make sure that our metal is overlapping our implant by 2 microns. So here we're seeing a different type of rule. Like we're used to minimum width. So we saw that rule yesterday. We know what a minimum width rule is. We know what a spacing rule is. But remember that little diagram that we had about the overlap. So, what is an overlap? How do we define an overlap? So here we're saying that this green metal has to overlap the polygon, the yellow implant polygon by 2 microns. And we saw where that came from back in the diagram is that we wanted to be sure that there was an overlap of the metal that's on the drain by the implant. So important to note that. And it's kind of easier to see in 3D, but that's the definition. And that's why we have this design rule checker, because it's going to help you obey those rules, because everybody can kind of see, yeah, okay, I've got a 5 micron wire, but overlap rules are a little harder to think about. Okay, so now we have another set of rules that have to do with the via pad. And this is the openings where we are trying to connect metal to the outside world. So it's an opening in the passivation to connect to metal. And as we talked about, there are two types of openings in our JFET process. One is the opening to the outside world for the gate, and the other one is we're trying to open for our via pads. So here we have a rule that the via pad is 5 by 5 minimum, and the spacing is 15 from via pad to via pad. But then we have to be sure that we are then also enclosing the via pad by metal by 10 microns. So in this rule here, you saw we had a rule on overlap. But in this rule here, we have what's called an enclosure rule. So that means on all sides, the metal has to enclose the via pad. And that's different than overlapping the via pad, okay? So that is rule 3.4 in your design rule table. Okay, so in this case, for whatever reason, we have rule 3.1, 3.2, 3.4, and that's a minimum enclosure. And it's the metal that has to surround the via pad. Okay. All right. So now we'll move on to the via gate. Here we have a lot of 5s in this process. So the minimum width of the via gate is 5 micron. We have a spacing from the via gate to the via gate of 15 micron. And then we also have a rule between the via gate to the implant of 3 microns. Okay. So that is a rule between the polygons that we draw on via gate and the polygons we draw on implant. And then finally, we have a rule between the spacing of via gate and the metal. So that's 3 microns. So we have these rules, and these are rules for, again, we have a little typo here. This is actually 5.1. So I think we corrected that in the design kit, but I'll correct the slide. So this is actually rules 5.1 to 5.4. Okay, so any questions on those physical rules that you have to obey when you're doing your design and how they connect to the fabrication? Because when you go to do your layout, you are putting down polygons and you're routing things, and you have to think about the rules when you're doing your design. So you kind of have to keep them in your head. Like here, for example, pretty simple, you know, the implant rules. Okay, I'm probably going to design my implants first, so they're kind of on the bottom. Okay, I know I'm routing my metals, but these via pads, the via pad is pretty simple too, because that rule only applies when we're at the periphery and we're creating pads. But these via gate rules are a little bit more thoughtful, because we have to think about implant, we have to think about metal, and we have to think about via gate to via gate. And that's why these little programmable cells that have been created for you by Priya are so helpful, because they already have the via gate in them and the relationship with the implant and the metal. So, you know, we'll talk about that later. But if you're going to lay out your own JFET, you have to respect these rules. And one of the things I recommend is looking at Priya's reference design and also her generators before you do your own design, just so you can kind of get your head around all the spacing rules. Okay. So now we have what I'll call other rules. And these are that the maximum dimension of the substrate, and that is, you know, what Priya was telling you, that you get a 10,000 by 10,000 block. So we have to make sure your design is within that. So we actually enforce that by a design rule. And then the other thing that we do is so that because we're checking the substrate, we make sure that your geometry is within the substrate box. So that means that you don't have anything peeking out over the substrate box, so that we know, your design is within the 10,000 by 10,000. And that's a convenient way to check that rule. Any questions about that? Okay, so now we're going to go back to the design kit, and we're going to look at these rules, and we're going to look at what was set up for you in these rules. And we saw them on paper, what they were. We saw them on the fabrication process, so that we saw that what we're going to be checking from the fabrication to the layout. But now we have to look at how does the design rule checker see this, and how are these rules implemented for your design. So I think we promised you a break every hour, and is this a good time, Priya?
Yes, our next break will be at 3 o'clock, right? So we are either we go another 15 minutes and take a break, or we can take one now.
How's the group feeling? Do you want to break, Priya, or do you want to go?
I think we could go for some more time.
All right. If you're fresh, I'm fresh. All right. So we're going to go for 15 more minutes. So our break will be pretty much in the middle. So now we're going to look at the design rules. And so we will go ahead and do that. And just like we did yesterday, and you are welcome to follow along with me, or you can just watch. As I said, we have provided the files to you so that later on, you'll be able to take these slides and you will be able to do what I did and check it for yourself. So kind of up to you if you'd like to do that. All right, so we're going to go to the Setup DRC window, and we're going to click on the edit icon, and we will also be then looking at the DRC rules. So that's the two-step process. You go to Setup DRC first, and then we choose the rules that we want to look at. So I'm going to go ahead and do that live because it's more fun than using slides. So I will go ahead, take a drink of my coffee here. Good stuff. Okay, so we're still in the design kit. So now I'm going to go over to the tools menu, to the DRC setup window, and I am going to click on that. You notice in this design kit, we have one rule set only one. And we are now going to go into edit the selected command file because we've selected it with this little checkbox. And we're going to go ahead and edit that guy. Okay. So now let's go ahead and look at the rules one by one and see how they're implemented. Okay, I'm going to start with the numbered rules, and we'll come back to the substrate rules. So if you want to look, I mean, you don't actually have to look at these rules, if you are if you're a designer, because they have been set up properly by the CMC and their team. But we want you to be aware of them so that when you run the design rule check and you get a flag or an error, you will understand the relationship between what you're seeing in the error dialogues and the actual rules. So I'm going to review a little bit about what we learned yesterday about the design rules. And then later when we actually pull up some designs, I took Priya's design and made some mistakes in it for you to find. So we'll be able to refer back to the rules that were put into the design kit. So the first thing you notice is that Priya has numbered the rules. This is good practice that the documentation that we gave you has the rules numbered. So in the actual design kit, the rule name here, this number corresponds to the documentation. So then we always give a little descriptive name so that then they're pretty obvious, right? So this one is the minimum width of the implant. So here we're looking at a minimum width rule. The distance is 9 and the layer is implant. So that makes a lot of sense, pretty obvious rule. Then we can look at a spacing rule. Again, if you get an error on your spacing, it'll tell you I have an error on 1.2, and then it prints it. So the thing that's nice is whatever you put in this box, that's what gets printed in the design rule log. So, please, for your own sake, just leave these rules the way they are, and then you'll be a lot happier. So here we're using a spacing rule. It's 11 microns, and the space is from implant to implant. Okay, so I'm not going to go through all of these because I think that they are, the metal rules are very similar, but let's look at some of them that are different from others. So here we have the minimum overlap of metal and implant is an overlap rule. And this is something that we specify. The thing about the rule type is it talks a little bit about what type of rule it is. So here it's the overlap of layer 2 into layer 1. So here it's an overlap of implant into metal. And that may be, I don't know how they specified that, but we'll give that a check. And then we also have something called an enclosure rule. And so let's see how different that is from 2.3. So here we have rule 3.4 is the minimum metal enclosure of the via pad. And if you see this rule type, it says the minimum layer 2 surrounding of layer 1. So here we have a metal has to surround the via pad by 10 microns. And that's what this surround is saying. So the rest of these are pretty straightforward, and you can see their numbers are here. And as I mentioned, when we do the design rule check later, we can choose to check all of these rules or check some of them. So when you bring in the design kit rules, we'll be bringing in the definitions, but you can choose which rules you want to run and which rules you do not want to run. Okay. A couple of other things that I'm going to point out that are, not specified by the CMC yet, is that we also have these little choices here. Okay, and we talked about these yesterday. So we could have chosen to ignore acute angles, but here, since this is not checked, anytime you have an acute angle on this rule, it's going to flag it for you. So these are by design. And if you remember when we looked at the Polymumps design kit, there were different choices than the ones that are done here for these particular rules. So now I'm going to talk about our substrate rules. Okay, so we were talking about the maximum dimensions of the rules. So this substrate rule, well, maybe we'll do this one first because it's a little easier to understand. So here, this rule that we saw that was written up in, in the other rules said that the substrate has to enclose all your geometry. So this rule was implemented in 3 different ways, or four different ways, that the substrate is going to enclose the implant, it's going to enclose the metal, it's going to enclose the via pad, and it's going to enclose the via gate. And this rule could have been written as one big and statement. We could have maybe ORed all the layers together and then just said the substrate has to enclose the or of all of the layers. But this is fine. This is an okay way to do it as well. So that's okay. And then this other one, the substrate max dimension, we are checking that rule actually by shrinking the size of the substrate, and by the size 10,000 10,000 microns, we're shrinking the substrate, and then we're seeing if once we shrink it, if there's any substrate box left, because if it is, that meant that the original box was bigger than the 10,000. So we actually have a not exist rule that tells us that if we have any polygons, once we have removed the 10,000 by 10,000 square, we know that the design is too big. So this is kind of a complicated rule. And as I said, you don't need to worry about how we created that rule, but you just have to know how to run that rule. And we will we'll talk about that when we talk about the actually running the design rule checker. Oh yeah, now I know how we got off track. We were talking about the minimum, the different widths and stuff. Okay, so the other thing that's a little bit interesting about how this is set up is that we can limit the number of errors that's reported per rule. Because what happens with this is if you make one mistake, you probably made it 1,000 times. So like if you have, you know, and this can happen like in a a big chip, there could be 1 billion transistors. And so if the person made a mistake once, they made it 1 billion times. So we can limit the number of errors that are reported per the rule to 1,000. And you can change this number to 50 or 4 or whatever you want, so that you don't have pages and pages and pages of design rule output. So that's a number that the CMC has set, but you can change that if you want to, so that you don't have to look at every single error. And I often do that because I want to find in general the rules that I've violated, but I don't want to sit through 1,000 errors. The other thing that question?
Can we set it to 0?
No, then you wouldn't. then if you set it to 0, then you have then that error would, well, you could. That means that you will see no errors on that layer. So you might as well just disable the rule. It's effectively disabling the rule. So if you set that to 0, then that rule, if it found 55 errors and you set it to 0, then it just won't report anything. So you should probably at least set it to 1, or just go over and disable the rule. But good question. All right, so the other thing that is being set here is the all angle tolerance. And that is set because we in Priya's design, as I told you, since she has all angle wires, when LEdit runs the design rule check, it may choose to move the location of some of the points and snap them to the nearest grid point. And so she knows, or they know, that the minimum snap grid was set to, the manufacturing grid was set to 1. So that's why they chose this number, because they know that the when the snapping happens, it will never snap more than 1 micron. And by definition, it's going to be less than 1 micron. So it's going to snap to the nearest grid point. And they could have even probably chosen a half here, because it's going to snap one way or the other way. So this number about the all angle tolerance is always related to the manufacturing grid. So this is another number that, even though it's in the design kit, you can play with it, because it's depending upon how many all angle wires you have. You may or may not want to look at all those errors, because the tricky thing, though, is, are the errors related to the fact that LEdit is moving your points, or did you actually make a mistake? Like we talked about this with Priya the other day, is that she had misaligned one of her cells by just a little bit, and the design rule checker found it and flagged it. And so we actually looked at it to see is it really that the design rule checker had snapped her grid points, or did she misalign the cell? And it turned out the cell was misaligned. So, you know, you can run it with and without the all angle tolerance. And I kind of recommend, until you get used to design, and if this is your first design, you know, really try to understand that issue. And so we will we'll talk about that. Oh, question? Oh, okay. Yeah. So do you recommend doing the DRC check by activating some rules and correct them? Yes, absolutely. I totally do recommend that. So the question was, you know, should I do my DRC check all at once, or should I do it kind of rule by rule? This process is so simple that I would say it's not as important as something like for polymumps or a transistor process. Like, you know, some of my consulting business, I have, you know, some of the big IC processes have hundreds of rules. So we for sure do them in batches. But I definitely recommend, you know, even for your designs is, you know, check your metals, you know, check your routing wires separately from the other stuff and fix those, make sure you get them right. Or, you know, concentrate on your transistors and, you know, design your transistors and get them right, because it really helps you mentally to, you know, focus on areas of your design. So normally you're designing the core, the transistors and stuff like that. So get them all design rule correct, and then worry about your routing. And why do we do that? It's because if you wait till the end, you'll forget. You'll say, oh, you know, I got to go fix that metal routing. But this way it helps you focus your thinking onto the interior of your chip, and you know that's all correct. Everything's good. Now you can stop thinking about it and think about the exterior of your chip. So I often, you know, if I have rules that break out like that, like the pad rules, I'll wait and check them later, and I'll focus on the rules that have to do with the interior first. But again, since you only have a few rules, it's not so important. But when you get to more complicated technologies, absolutely, I would recommend it. Just don't forget to do the final check at the end, where you look at all the rules. Okay, hopefully that answers the question. All right, we're back in DRC land. Let's go back to that. Okay, so I'll go back to the setup. We're almost through the setup of the DRC. So I just wanted to talk about, we're talking about some of the options in the DRC. So we talked about the all angle tolerance, and in the exercise that we will be giving you, I kind of showed you, I started that exercise yesterday on how to do the DRC. And we have you know, we're going to give you that exercise so you can practice at home. And you will see the effect. One of the rules that we have is affected by the all angle tolerance. So you'll be able to practice and understand where that tolerance comes from, and also, you know, when you would use it properly. So we'll definitely have some takeaway homework assignment for you to play with. Okay. So a couple of other things about this screen that I wanted to point out. We talked about the errors, we talked about the tolerance. Then the other thing we wanted to talk about, which kind of gets to the question that was asked earlier, is we have these things called geometry flags. And so let's talk about them. We didn't really have time to talk about them yesterday. So if you are doing a design in a technology that does not allow some of these things, then you really want to flag them and be aware of them. And one thing that, you know, we should probably check on with the CMC and 3IT is, do they allow acute angles? Because some fabs do not allow you to have polygons that have acute angles. And why is that? Because if you have an acute angle, you can have a very small sliver of material that might break off in the fab. And so some fabs, you know, can handle the acute angles because they have biased the design rules, and they've got a lot of other ways to deal with them, and other fabs just don't let you do it. So one of the things that you should be aware of is if your fab is okay with acute angles, you've been working with that fab, you might turn that flag off because you really, you could get hundreds of errors that don't matter, or, maybe they matter, or maybe you want to make sure you don't have any acute angles, because acute angles are never good. They're just asking for reliability problems. But, sometimes it just doesn't matter, right? And if you're doing a design in the university or, pre-production, you don't have to worry so much about reliability. So that's a flag you may turn off, because then you don't have to sit through the errors. The all angle edges, again, most of the designs that we have are probably going to have all angle edges if you do routing like Priya's. So that's going to flag. The off grid, here it's reminding you that your grid is a micron. Again, good design practice. I always like to design on a grid, but if you have all angle stuff, you may have polygons that are off grid. And you can decide for yourself whether you want to turn that on or turn that off. And so that's something that you should you can actually play with that. I'm asking you not to change the design rules themselves, but these geometry flags, they're kind of for you to think about your design. This one is really great to know. The zero width wires, why do we even see them happening? Well, what happens is that, as you know, in Edit, if you are drawing something and you mean to draw it, and if you don't go back to the pointing tool, you will draw and keep drawing. So what happened in the very beginning of Edit, and still happens today, is that people draw a wire and they draw another wire and they draw a third wire and they go, okay, I'm done with wires. And they forget to leave wire mode. And by mistake, they actually, make a wire, or they forget to set the wire width, or something like that. So then you can't see them. So these wires you can end up with things that are not good for your design by mistake. And so Edit will find them and flag them, and you can then use the error browser to go find them and kill them. So the other, this is a companion rule here. And then the other thing that you may or may not care about is, as I said, if your GDS writer has more, it allows you to have more than 200 vertices, then you don't care about flagging them, either the polygons or the wires. So as I said, probably the 3IT doesn't care about that, but we will clarify that. And then these are also important to notice. This one, you cannot turn it off, this flag self-intersections. And why is that? You can, by mistake, make a polygon that intersects itself. And those are always bad for, going into your mask shop. And the reason why is if a polygon intersects itself, then you will, maybe the fab can't tell what the inside or the outside of the polygon is. So we have an application note on self-intersections, but one of the things that if you see one of these in your, if the design rule checker flags it, you pretty much have got to fix that problem. And I'll show you later when we're messing around with the design, I'll show you, what a self-intersecting polygon is, but pretty much it's a polygon where you draw it and then you come back around and draw over it so that it intersects itself. And then there is, you can also, flag these round or end wire styles. So those are for when you are, we won't be talking about that in the class because we're going to use a conservative wire style. So you don't have to worry about that. You should never see this. But those people who have certain types of end wire styles, it would flag those. So the geometry flags, you can set them on a case-by-case basis as you run the design rule checker, and we'll do that when we run it. Just wanted to make sure you knew how to find that information, and it is right here in the geometry flags. It is also, if we close up the design, we also see that there is a check geometry flags option in our in the tools. So if you want to just check your geometry flags, like for me, when I do a design, before I even run the design rule checker, I want to find any self-intersecting polygons. And so especially before I write my design database out to GDS2, I want to check for self-intersecting polygons. So I will often check the geometry flags by themselves before I GDS out, just to make triple double sure. Okay. All right. So that was about the DRC that's inside the design kit. Now let's talk about, let me go in here just to make sure I didn't miss anything on the design rule check setup. Okay, we got our design rule set. We talked about that. We talked about how to open them. And then they have left all of these runtime options options blank, right? And I think Priya, my understanding is that you guys are expecting the students and the people using this design kit to run their own DRC, and then you will run it also, right? Is that correct?
Yes.
Okay. All right. All right. Great. All right. So up to you. You can choose the PDK is silent on this. So if you want to set it up so it sends an email to you, or if you want to run it in the background so you can do some more editing while you're running the DRC, you can choose to set these things. But in general, these, as we see, we will actually run the DRC a couple of times. It's pretty quick. So I don't think you have to resort to, having it send you an email, but you can do that if you like. Okay, so the other thing that they've done in the PDK, which is really good practice, is in the list of cells, there is a cell for each rule. So you can see the rule, like if you want to understand it, and see it visually, because when we looked at the rule list, we saw it textually, but they actually have provided for each rule a cell that you can open up and understand. So for example, in this one, they have chosen to show you the correct rule, or the rule that is it will not cause a design rule violation. But I like to have both a correct and an incorrect rule. So for example, here, this rule is that the thing has to be 5 microns. So I would also include a 6 microns by 6 microns. And then when I run the checker, I will see that it flags one and not the other. But they have shown you here the correct rules. And so the reason why this will help you is that if you want to, you can run the design rule checker on just these rules in these individual cells. Because one thing about the design rule checker that has to be clear is that you can run the design rule checker on any level of the hierarchy. So I can run it, this is her full reference design. But if I want to just open this DRC rule here and run the design rule checker on it, the design rule checker by default runs on the active cell. And what's the active cell, as you can remember, is that if I have a darker blue background here, this is the active cell. Or if I come over here, this is the active cell. So the design rule checker is going to run on the active cell. So it will, it knows which one you're pointing at, and that's the one that it's going to do. And as we also talked about, if you don't want to, if you're not doing like anything particularly hierarchical, you can also, we'll display this later. You can set up a box and just run the design rule checker on a subset of your layout. Okay. So any questions about the PDK view of the design rules? Because we will then switch and start looking at the design, using the PDK from the designer's point of view. So now we were checking the design rules. So we were taken a look at those. So now we are going to look at some files that I made, and we're going to run some design rule checks on a design that is correct, and we're going to run one that is incorrect. Then we'll probably start looking at the reference design. So again, you can follow along with me if you like, or you have access to these cells on your Dropbox. So if you want to do what I'm going to do at a later time, you can do this. I think this is being recorded, so you'll be able to follow me if you like. Okay. Okay, so I'm going to go ahead and close the design. I will not save anything. Discard them. Okay, so I'm going to open a design that I made using Priya's design kit, and I am going to show you, what I did, and we'll run the design rule checker, and then we're going to start with a blank design, and we're going to learn how to attach to the library and to start the tech file, just like we learned yesterday. But what I wanted to show you was a design that has already been set up, and we'll play with that. So if someone happens to give you a design that has stuff in it, then you'll know. So this is my JFET design.tdb. So if you wanted to open that, you would go File, Open, and I have given it to you in the Dropbox if you want to do that, or if not, you can just watch me as I play with the design. So I have done a couple of things. I have attached to the technology, and I've also set up the library. So let's take a look at what I did. So if we go into Setup, Design, you will see my technology has been set to the class technology. So I have all that in there. And I've also set up so that I am using the class PDK as a library. So, and I unimaginatively just gave it a name that is derived from the TDB file name. Okay, so you will show you how to set this up on your own in a little bit. But that's what I did. And then I also, here is my library. You can see this is in blue. So all of these cells came in from the PDK. So this is all, all these cells are notated as blue because I cannot change them. I can just use them. Okay. And then I created a copy of Priya's reference design, which is here. And later on, we're going to show you how the difference between copying and instancing and why you want to do one versus the other. So I grabbed her design, and I made her design, and I have a cell that's her design, but I took out the CMC logo because I want to show you how to design rule check her design. But as I told you, the CMC logo has all kinds of stuff in there that will not pass the design rules. So I removed the logo from her design. Then I also made another copy of her reference design, and I made a mistake in it so that when we run the design rule checker, we will get some errors. So we will now go through, run the design rule checker, and find the errors that I made in my bad design. And but first, we're going to run it on the good design, because we'll see if Priya made any mistakes in the reference design kit example. So I'm going to go ahead and open that design, from which I have removed the label. And we are going to go up and we are going to run the design rule checker on that. So as I told you, it's going to run on the cell that's active. That's why I have it open. And I am going to go in and, I'm no longer in the design kit. I'm in my my cell. So I just want to check and make sure the design rules are there, and they are. So it's going to check all these rules, and I'm going to leave everything exactly the way it is as it came in from the design kit. So then I've checked and make sure I know what's going to happen. So which rules, I'm going to check them all. And I now am going to go ahead and run the DRC. So you can see how fast that ran on her complete design there, right? And you can see the output results that came into the verification navigator, okay? So the verification navigator popped up automatically, and it gave me a bunch of errors. And so she has 140 polygons and wires with acute angles in them. She's got a bunch of all angle wires, which we're expecting, or all angle edges, which we're expecting because she's got all this all angle routing. And she's got 639 off-grid objects because she worked with all angle designs. However, these things are not going to stop, her from having a clean design for the fab, because these are informational, information that she knew she had, that she had these all angle edges. But if you notice, there are no errors that are flagged by number like they are in the design rule list. These are all what we call geometry flags. And if I wanted to, I could go in there and in the DRC setup, I can go ahead and modify the geometry flags and turn those off, no longer flag the acute angles, the all angle edges. And what did we do with the polygons off grid? I could flag those, turn them off, click OK, click OK, click OK, and I can run it again. No errors to display. So all of that came from these geometry flags that we have. I recommend leaving them on, just so you know, if you weren't expecting all angles, then just it's a good practice to have. But if you really want to, make sure you have clean things and you know which things you turned on and which things you turned off, that's okay too. So now let's go and look at our bad design. So Priya did a good job, nothing wrong with her design. Okay, so now let's close that up. And now let's look at my bad copy. So I have made a mistake in this design somewhere, and this looks pretty much like Priya's design, but I made a hidden mistake in it. So let's see if the design rule checker can find that mistake. Okay, any questions about what I did so far? Okay. So now I'm going to go in, and now I have a different cell open. So now I'm going to run the design rule checker. And you can see now that I have made 2 mistakes in my design. It has flagged those 2 rules, and the verification navigator has come up. And you can see I violated the minimum width of metal being less than 5 microns. And I also violated the metal to metal spacing. And we don't know where, but we're going to find out. So this is, as we talked about it, we could go ahead and expand the plus key here, the plus thing. And it's telling me that I made 2 mistakes. And so I'm going to look at where I violated the metal width being 5 microns. So I'm expanding my, I'm going ahead and expanding my verification navigator hierarchy, and I'm going to click on the first error. So it's here, it's telling me that my width was 4 and the rule is 5. So the little 2 here means how many errors, and the little thing in a little bracket is the actual value that it calculated that your geometry used, and then the rule is quoted here. So that's why, remember when I showed you the rule names, that's why Priya and her team, gave them a number and kind of a name here, because that's what gets printed here. You know, if she had not put the number here, then you'd have to kind of remember which one it was, or if she just, you know, gave it some other name. But the practice is to always number your rules, give something that is logical, so that people can remember, okay, that's a minimum width rule, because that is under the control of the PDK designer. And someone asked earlier, we're going to talk about how do I make a good PDK? Well, this is why this is a good PDK, because the design rule errors are being displayed in a logical way with good names. So now I can simply click on this guy and it's going to zoom in and find the error for me. And the thing that's really great is that I couldn't see that I had this little, you know, this little piece of, you know, metal hanging out there. And if I'm using my minus key now, I'm going all the way in, and you can see that at the bird's eye view, you would never have seen that, right? So now I'll go plus in, and it's flagged that that piece of metal is only 4 microns wide, and I put it in some arbitrary place. So now let's look at the second error. It's actually flagging the opposite sides, because I made a 4x4 piece of metal. So if I had made a really long and skinny thing, it would only have flagged one of the sides. So now it's zoomed in and it showed me where the error is. And it did that based on me going into the design navigator and pointing it out. So I violated 2 rules here with 1 piece of geometry, very efficient of me. So now if I look at the spacing rule, I only violated that once. And so here, it's now showing me, if I have a spacing rule problem, it's zoomed in and it showed me the 2 edges that are violating the spacing. So it found this edge here and this edge here are being flagged as not having the correct spacing. So it's saying that I'm supposed to have 15 microns, and I only had 1.776 microns in my spacing to my little square. So now, you know, I've got to go in and fix this because this is a problem. So I can now, you know, find that little box. I can select it, and I can go up and edit it, and I can cut it and, you know, fix my error. And now if I run the design rule checker again, there are no errors to display. So design rule checker, having that browser in there is really a lifesaver, because it's going to, excuse me, it's going to help you find things that visually, you know, just by eye cruising around your design, you may or may not find, right? Because this is actually, you know, a very large design, and I have to kind of look in, you know, so it's not a bad thing to crawl around your design yourself, but you should also, you know, use that design rule checker to do the work for you. Yeah. Any questions about what I did so far? Because you have access to these files, and you will be able to we'll send you the full set of slides that show you the step-by-step, you know, mouse clicks that I did as an exercise. And but I just wanted to have you see it so you can kind of get the concepts of it, and then you can practice on your own when you are you know, when you're on your own. Oh, okay, good. Thank you. All right, so the verification has been completed. So we are good to go. All right, now we want to go in, and I have shown you, these are my bad designs. This was, you know, my bad design. So now what we want to do is we will create a new design, and we'll review what we learned yesterday of how do we start a design from scratch, and you know, use the design kit as a library, and also you know, how are we going to work with it as a library and as bringing in the technology, because in this design, my JFET design, I already did that for you, and the purpose of this was to just show you the design rule checker because I had already created these designs for you. But now we're going to set up the technology and set up the library, and we're going to look at the various methods for interacting with the design kit. So I'm going to end the discussion of the design rule checker, and we will probably not revisit it again unless there's questions, okay? As I said, there will be exercises for you to play with this on your own later. Okay, so that was my, I had my bad copy, my good copy, and the takeaway from this is do not design rule check the logo. And also, if you put any text in, maybe you put some text in there using the text generator. The one that CMC had in there with the octagon and the technology numbering, that probably would pass the DRC. But if you spell out your name or whatever in metal, you should probably remove that for the design rule check. Okay. All right. So let's go, and we're going to close this design. Do not save. Yes, I really want to remove my edits. Okay, so now we have a clean edit, and let's go back to the slides. We have a few minutes, so we will start this next section. Okay, we executed the design rule check. We did that. Now we're going to talk about attaching to the design kit. So if you remember yesterday, probably in the second section, we talked about how do we attach to a technology and a design kit. So we are going to go do that now, and you are welcome to do it with me, or you can just watch. You have these slides, so you can do it on your own. And after we attach to the design kit, we're going to check and make sure the design rules are there, and view them just to make sure that we understand how that works. And then we're going to set up the library. Okay. All right, so let me turn to the to edit, and with our blank edit. And so now, instead of file open, which we've been doing for a while, we'll go back to file new. So now we're going to do file new design. Okay. And I will pick a new name. How about test 23? Okay, so we would pick our design file name. We can browse to the directory using the ... or we can directly type in the name that we want. And we can set a technology reference. Before we would have none if we were making our own technology. But in this case, we're going to set a TDB reference. And just so that we can show you where we're going with that, we are going to use the design kit that I gave you. Where is that design kit? Is it here? Yes. So the one that we have on the Dropbox for you is called ESP JFET PDK V3_alpha_class. So that is what we're going to use as our technology reference. And so, as I told you, we typically divide up information that comes from the fab into 3 files. One is a technology file, one is a library, and one is a reference design. So the reference design can use the library can use the tech file, but the CMC, to make it easier for you, since this is a fairly, a small technology, they have put everything in the same file. So we can, you'll see that I'm using the tech file name is going to be the same as the library name, but you don't have to do that when you're making a design. And because someone asked about, how do you make these PDKs anyway? Typically we put all our technology information into one file, and that's the thing that we would be putting in here. And just to echo, we reviewed the design kit. We've got the grids, we've got the layout definitions, the colors, all that stuff. And if I don't linked to a technology, then all my layers are blank, right? So we have a TVB file with this technology reference. And you can see here, one-time import. Just to remind you, we're going to leave that unchecked because we want to, if the CMC decides to change something in the technology, we want to make sure that our file will just automatically read in that new technology. So information. So we want to do we want to create a technology reference. Now, one of the things that may happen is that the CMC may change the name of the file, in which case we'll talk about what to do there. But if they have just an update to the same file name, then this TDB link will just keep reading it each time. So that's very convenient for you. Okay, so now we have our technology that was brought in. So if we go to cell open or cell new, we can create a cell. And you'll notice that until I made a cell, nothing showed up in my layer palette. And that's a difference with the old technology files from Tanner. Is in the old days, Tanner would by default make a cell for you and show you the layer palette. But these new Tanners, since, I don't know, past 5 years, you have to open a cell to get the technology layers to show up. So if you noticed, I by default got those technology layers that we're used to seeing. Now I'm going to take a quick peek. That's what I always do. I check my design. I check my technology. Yep, I got it from the class. I have the right microns. I have the right grid, the right manufacturing grid. Okay, things are great. And then I take a quick peek at the DRC setup. I'm just going to pop in there. Yep, looks like my rules are there. Not going to touch anything because we're done with the design rule checker, but I just want to make sure that my technology came in okay. Because sometimes in Edit, it can get into these weird modes. I don't know what I'm looking at. I just want to make sure maybe if I have 2 files open at the same time, and I don't have what I think I have. So I always just check my colors are okay. My information about my technology is okay. And my design rules are there. So now I've got to go set up the library. So I am going to go back into setup design. And I'm going to go to the libraries tab. Okay. So, excuse me. I now am going to click on the path here, and it gives me this little browser. And I am also going to call up the PDK as my library. And as I said, I'm boring, so I'm just going to let it choose the name for me, which it chose automatically, but you can edit this, if you don't want to, have the alpha class there, you can do that. So now, as you saw, let's make sure we save that. It's got that library with that path, okay? Okay, so the next thing to do is to go over and we are going to now view the design navigator. Because now we want to make sure that we picked up the library and we picked up all our cells. So here again, I have in blue all the cells from the design navigator. So what I can do now is I can start to put these cells and use them in my design. So the first thing that I'm going to do is look at the parameterized cells that that Priya created for us for the gate and the JFET. Okay, so we'll talk about those, and I'll enlist Priya's help to discuss them a little bit. So the first thing I'm going to do is grab the JFET parameterized cell, and I'm going to drag and drop it into my design. So there you can see it has asked me what is the length and what is the width of my parameterized cell. So I'll go ahead and accept the defaults, and it's thinking, and it has now put a, I'm actually just zooming. It has actually now put a parameterized cell into my layout. So Priya, do you want to talk about what's in your cell? What it actually did?
So the entire JFET cell that you have to design, now just with 2 parameters, it populates that.
So what layers did it give you automatically?
So the red layer is the gate one. You could just zoom in and.
Yeah, I'll zoom in. Oops, sorry. The zoom key isn't working so well today. And maybe what I can do is I can turn the layers on and off for you. You want to see the gate?
Sure. So it has the metal layer, via pad, and the via gate.
Okay, so this is the gate that it generated. And is this the thing that is, what is the dimension of this gate?
So the length of it is what, when you populated this parameterized cell, whatever you gave, that's the length.
Okay, so can you guys hear her okay? Because I'll repeat what she says if you want.
Is it just?
Couldn't.
Say again?
I couldn't hear Priya.
Okay, I'll repeat her. Okay, I'll ask her, and then when she says something, I'll repeat. So she has the number that you specified when you ran the parameterized cell is setting the gate length, I believe. So that JFET that you just generated there, that is going to be 1,000 by whatever it was, I think 5, right? And so she put down a polygon that's 1,000 by 5 representing the gate. Okay, and then let's turn on the implant. Oh, sorry, the implant is the orange, the yellow, right? Okay, so she now has some implant polygons that she put down there, and she obeyed the design rules so that they were correctly spaced off the gate. And then I believe that she also put some metal in there. The metal is then been correctly spaced with respect to the implant. And then I think there is no via pad here because there's no pad. Is that correct, Priya?
So yes, so this is emulating the source, drain, and the gate from the top view if you were to look at the ESP, the sensor structure.
Right. So this is something that you can think of this as a transistor generator that she has created for you. So then your job would be just to correctly connect to these structures. Okay. So then, as we talked about, you might say, oh, you know, I really didn't want 1,000 there. We will go in there and say, oh, made a mistake. We can just select the object, and you can see it's selecting JFET parameterized cell auto. And we can go in there and we can edit the object. And it's going to ask me, you know, what do I want to do now? And I can just say, well, I really wanted it to be 500. I made a mistake. And so now it has modified that JFET parameterized cell. So this one is 500. So that's something that you can do. And then the other thing that may be helpful to you, we don't know what your application is. That's why maybe we'll talk about that later, is maybe you would like to have an array of these JFETs. Well, then we can edit the object and we can go into the instance parameters and then create an array of them in some way. So we can make arrays of the, you know, we can set the array parameters and we can also set the, you know, if we regenerate the cell, we can regenerate the structure. And if you want to, you know, if you want to say, okay, well, I'm in my 500 one and my simulations tell me I need another one that is, you know, 250. Now we can put one of those in there. And, you know, now you can start to see how, you know, we've got some structures going on and we might want to use the alignment tool. to align these guys so that they're aligned on the edge, right? So we can start to think about how we can use some of the features that we learned yesterday for alignment, for moving things around. If we're working with this higher level geometry, we can move stuff in ways that we can, move things clearly, because, now these are pretty big structures. And if I just grab this instance, how do I know whether I've moved it correctly to go edge to edge with the one that I already drew? I'd have to zoom in and then figure out, what I do, that sort of thing. So if we use the alignment toolbar, we can get a lot more power of, into how we align things. And then you can also see the scale that we're starting to work at. If we make those little if I make a little mistake and make that small little metal box, I can end up with a problem that I have made a very small mistake, but I can't see it. So then I will have to go ahead and run that design rule checker. Priya, is there anything else you want to say about the JFET parameterized cell?
Yes, so one thing when you're instantiating the cell, I think Marianne mentioned this yesterday, but just you do not have to again add microns to that. So you just have to add the numbers, because do you want to show that, Marianne? Because initially I think I did this mistake and I added microns. So it does not throw an error. It creates a very, very, very small cell that you cannot really see. So,
and Priya called me on the phone and said, "Oh, it's not working."
Yes. So they already set to micron. So you just have to say 250 micron. And right now, the way they are, it's not like your conventional channel length and the conventional channel width. This is a bit reversed. So here our definition of length and width is opposite to what you would conventionally see. So just to keep that in mind.
Yeah, and we may want to update that in the design kit. We can we can put in parentheses, blah, blah, blah. This is the width or the, whatever it is. So we can make some pictures and stuff like that. But right now, for this class, the purposes of this class, we just wanted to show you the concept of how it works. But we'll document that and get it clear for you. But yeah, absolutely clear. This is already in microns. And that being said, just to if you ever decide you want to learn more about how these parameterized cells are done, we do have an advanced class, and Priya chose to put this in microns already, but you could have made it be scientific notation if you wanted to. I find it convenient to not have to type e to the -6, but the generators could be made so that you enter it in MKS units. So it's up to you what you want to do, but she did it the way that most people would think of, which is to think about it in microns, because all the numbers we've been talking about so far are in microns. Okay, great. Yeah, it's really good to remind people of that. All right, so that was the JFET parameterized cell. Let me give myself a little bit more screen real estate. We also have another parameterized cell that Priya has given us, which is the gate parameterized cell. And that, as far as I understand, just makes the gate layer, correct?
Yes. Yeah. So the previous one generated this configuration of the source, drain, and the channel. So if you see, go to my reference design for the 5x5. Not the array,
Oh, I'm so sorry. Yeah, I'm sorry. You're right. This one?
Yes.
Yeah, sorry. Do you want me to zoom in?
Yes, please.
More, or is that good?
A little more. So what I have done here is, instead of creating the conventional structure where, you have source, drain, and that gets connected, like towards the pads, probably. Just you could move left. Yes. So the middle structure.
The middle structure is just the gate, right?
Yes. And the second layer could either act as a drain or a source. So it could be like source for the first transistor and drain for the second one. So So I have not used the JFET, the parameterized cell for JFET, the complete structure, but I have created these layers on my own so as to maximize the real estate on this chip.
Right.
So that was the reason why I provided one more gate parameterized cell, because if people wanted to go ahead and design on their own, they could do that.
Right, exactly. Okay, sweet, sweet. Okay, and we'll cover more about this. In the next section, we're going to talk about the reference design. So good, we started to pull it up. So we are going to talk about the reference design, how Priya created it, and then also, why she did what she did. And that will help you when you're thinking about your own designs, to do some best practices. So I think that is time for West Coast lunch, right? Is that right?
Yes.
Great. So the plan is we're going to give you a half-an-hour break, and then we're going to come back and we're going to look at the reference design, see how that was done. Then we're going to look at some other designs that were done in this technology, because so far we have beaten this one to death, right, Priya? And so we'll look at some other designs, and then we'll talk about some best practices that we learned from talking to those designers about those designs. And then there was a question about, how do these PDKs get created? So Priya is going to give a little history about the technology and the PDK, and then we'll also talk about what's likely to come next in terms of the PDK, so that as you work with this technology, things may change a little bit over time, and so we may be sending you a new version of the PDK, and what do you do about that? So that's the fun of working with new technologies, because things do change, right? If you're working with TSMC on some well-known technology they've been shipping for 10 years, nothing changes, you just grab the design kit and go. But here the documentation may improve and stuff like that. So anyway, thank you for your patience as we do that. So let's give you a nice half-an-hour break, come back with questions, and that's what's coming next. After we look at all of that, we will then do a section on output. We'll talk about GDS in and out, because Priya would like you to be able to know, so far we've been working with a Tanner database, which they can accept at CMC, but she would like you to learn about GDS in and out. So I'll cover that. And then we'll learn how to GDS in and out this design. And then after that, we will likely have some words from you guys about what you want to do with this technology and how we can best help you. So that's the next section, next couple of sections that we're going to talk about. And then if there's more stuff that's on your mind, we will, we'll do that too. So we may, if we're lucky, end up a little early today, but we'll have to see how the afternoon progresses. Okay. So far in, we set up the technology, we set up the library, we showed you how to bring in the programmable cell from instance the programmable cells that Priya did. And we can also just, slap in any other cells that are not programmable into our layout. Like, if we wanted to just grab this pad cell, we can just drag and drop that one in there too. And you can see it just came in as geometry instead of the cell, the programmable cell. So in that case, now we have a little pad in our design. So one of the things I wanted to talk about was that we are, in this method, we are instancing a cell out of the design kit into our design. So our design was called Test 23. And if you look at the browser here, my design kit is here with all of these cells. My design cell 1, which is in my Test 23 file, contains some geometry that I pulled out of the design kit. I can also go over here and pop in some geometry that I designed myself. Here's some stuff. So now I have a mixture of stuff that came from the design kit, stuff that I did myself, and I can create my own cells. Now, one of the issues is someone said, I see this nice reference design from Priya, and I want to change it. What do I do with that? Well, I can open this in my edit session, but you can see it says read only. So I cannot edit this reference design because I'm pulling it out of the library. And so I can instance it in here into my design. Like I can go ahead and shove it in there, but now it's an instance. So I can go ahead and change its translation and things like that, but I can't really go in and edit it in any way. So I'll just go ahead and undo that. So what happens if I wanted to take Priya's design and put it inside of my design and then change her design? So, if we're doing something like a pad or some, parameterized cell like a gate or a JFET, we don't really want you to edit those because they came from the design library and somebody, Priya correctly designed those. But the reference design, it's kind of like a starting point for you. So, you probably do want to edit it. So what we do then in that case is highlight it in the design navigator. And then you can go into cell and you'll be able to do a copy cell. In this case, let me go over here and let me go ahead and open it. It'll be easier to do it this way. So I can go into copy cell, and then I can copy the cell from that library into my database, into my design. So it'll put the word copy on there, and then it'll shove it into your database. And then now that it's a copy, you'll be able to edit it. So that's the problem here, is that if you, if you are looking at, using the reference design within the design kit, you can't edit it. So what you have to do is then copy it. So there's two things that you can do with this design kit. If you're using these atomic elements like the pads and the different smaller devices, then you want to really keep that reference going, because if Priya changes the cell, the programmable cell, to do something new and cool and different, you'll pick that up because the library will automatically change. But if you are using her reference design like as a starting point, then you may want to copy that into your design and copy its hierarchy, or maybe just copy the top part of it and keep the references to all the library cells. So you have to kind of think about how you want to use the library, and that's one of the reasons why we may in the future have a reference design that is not inside the library, so that you'll be able to copy it more easily. And use it more easily. But that's one way around this problem, that you cannot edit the library. Now, as I told you, you could, and you probably should not, you could go ahead and do file open and open the design kit and modify the design kit. But we really don't want you to do that, because then you have two copies of the design kit, your design kit and the one from CMC. So if you really want to use something and modify it from the library, just copy the cell into your design and then modify it that way. Okay, does that make sense? Do you have any questions about that? Because it is kind of a thing.
Sorry, I just missed the part, like what's the exact step to copy?
Say that again, please.
Can you just show me like how you copy the cell? Because I think
I
missed the...
yeah, sure.
Sorry about that.
Yeah, no problem. No, that's why we're here. This is the copy cell command. And L-Edit has L-Edit has this used to act a little differently. They used to go through, maybe if you're an old L-Edit user, copy cell actually used to bring up a dialog and you had to choose the cell that you wanted to copy. But now L-Edit has this new thing that it tries to guess what cell you want to copy. So here, because since I was playing with this cell, it thinks you want to copy cell 1. So you have to go over into the design navigator, and then and sometimes it doesn't even pick it up right. So I often will open the file that I want to copy, and then when you go into cell copy cell, it will it will try to pick up the right thing to copy. So this is it's copy cell here, and that's the way you can get cells from the library into your design, because it asks you where do you want to put it, and then you can put it inside of your design. Okay, so it's under cell copy cell.
Oh, okay. I think if you right click the cell to copy in the navigator.
Maybe sometimes it works, sometimes it doesn't. There's a lot of.
I never get the menu with copy the cell when right.
Yeah, I know, because I don't, I tried right clicking myself, and there's the save cell to TDB file option here. Yeah. So I can save it into a new one, but I wasn't able to get it to allow me to do a copy cell from right click, because that's exactly what I tried. And so I had to go up to the cell copy cell, and so there's a way to do it, but it's just not straightforward in this from this interface. And the library navigator may make that a little bit more straightforward, but the idea of it is to make it be a little bit more of an idea that you're going to use the cells in the library by reference. So they make it a little bit hard to copy between the library and the library and the other file. So it's but there is a way to do it. Let's see if we can do it from the library navigator. Okay, so I can copy. Yeah. So if I go into the library navigator, that may be a bit easier. Go into view, docking views, and turn on the library and cell list. And you'll see, I actually toggled it. So let's go back there. If you see, I have a design navigator, but then I also have a library navigator. So if I go into, the library navigator, I can then, it looks like I can get my copy from there. And it says, where do you want to, we have a cell name here. Where do you want to put it? And I'm going to put it from this library into my design. And it's going to call it _copy. And then when I click OK, it should go in there. So now I have it available to me, and I have it available in my design, and you can see it's editable now. So it looks like if you want to really do the copy right, you should go into the library navigator, and the library navigator will then allow you to copy by right clicking in between the two. And so to answer the lady's question that was talking about copying between two TDB files, this is a way to do it. It doesn't have to be a library file. It could be, you could have two design files open as well. The library files are special because they come in, read only, but you could have two design files open, and then you can copy between them. But I just wanted to make sure that everybody was aware of this, because if I try to edit directly, I can double click on this cell, but you can see if I double click on a library cell, one of these blue cells, it's just not going to allow me to edit it. Whereas now I've got Priya's, reference design here. I've copied it, and you can see that reference design is editable, but it's still calling out the cells that she used from the library, and it's maintaining their references. So the raw geometry at the top level, I can edit. I can remove that stuff, but it's still using the library pads that I had before. So when you do the copy, you can either copy it and get all the geometry out, or you can keep the library references, which is what you want, because now I have a top level thing that I can edit. I can edit this guy, and maybe I want to move my JFETs around. I didn't like where she put it, so I'm going to put it over here, but I'm still using her her reference cells from the library. And so we can do this either hierarchically and let everything be a new cell, or we can keep those references at the lower level to the library, which is probably what you want, because you probably wanted to still have all these pads, but you wanted to maybe change her design a little bit, right? So in this case, you'll be able to change her routing and keep her JFETs, or maybe you don't. You'll be able to also just delete these JFETs from that design now, and instance some other JFETs that you did, or draw them by hand, or whatever you want. But this is really a key issue that this one here. That this reference design that we have here, where'd it go? This is the blue one that's inside, read only. But since I copied this guy and I put it in my design, now I can edit it, okay? So that's a pretty key issue. And her reference design here includes the same pad cells, which it's pulling out of its own library. And my copy now is also including the same cells, which it's pulling out of the library. So pretty important thing to know. And it looks like the best way to do the nice copies is with the library navigator. It can be done with the design navigator, but it's, I think it's a little buggy that it's not giving you the right cell to copy. So I think the library navigator is a little bit more robust for that. And as we talked about yesterday, they seem to do the same thing, the design navigator and the library navigator, but they have different purposes. The design navigator is kind of focused on the cells that are in your design and, being able to, instance them and do stuff like that, where the library navigator is more for browsing the library and seeing what cells are there. And there's a lot of processing that you can do with the library navigator. And we didn't really talk a lot about that because I had to make some choices as to what we were going to talk about in the basic class. So we kind of focused on the design navigator because that's more often used. So anyway, I'm going to end this section here, but I want to make sure that I answer any questions about how to work with libraries, because we're going to move on to now talking about how to export your design in GDS. And so it's going to be more about importing, exporting, and then we're going to look at the reference designs. So of course, if you have a question that comes up, I'll answer it. But if you have something specific to the navigators or the libraries and how to use them, please ask it now.
Are all cells added to the library automatically, or I'm not quite sure about the cells in navigation. Sorry, the design navigator and the library navigator. Like this, do they have the same number of cells or identical cells in these two navigators?
Mm-hmm. Yes. You can see here in the library navigator, they have, it's not displayed hierarchically, right? Right. It's displayed in a little different way. but yeah, the idea here is to, in the library navigator, you're kind of looking for the name of a cell, like, oh, do we have a pad cell, pad 100, whatever it is. So the goal of that library navigator is to find a single cell by name, but you're not really necessarily concerned about the hierarchy. So the design navigator is all about the hierarchy. So the electrode cell here is used in, this one, the electrode cell is used here, so it's showing you the same information a lot of times, because you also, here's the raw electrode, right? So here it's showing the hierarchy, so that cell is repeated many times because it's part of many others. But if you look at the library navigator view, we're just kind of looking at the cell list. So it's like I closed up all the, the hierarchy here, right? That, if we close these all up, you would have very similar looking lists. But here it's the library navigator is more about, this other stuff. Like here we have the 4 cores, here's the cores, then we have all the DRC rules. So that's all the same, right? And then we have the electrode, that's the same. Then we have the gate stuff, and then the JFET stuff. So the list is exactly the same. It's just the design navigator is showing it to you hierarchically, and the library navigator is showing it to you in a quick view so that you can just say, oh, I know Priya told me that's in design rule 1.1. Yep, okay, that's in this library. So does that answer your question?
Yeah, definitely. Maybe one, sorry for the questions. Maybe the last one. When a cell is created, is it automatically added to both of the navigator, or
yes,
both of the navigators?
Yes, it is. And again, you're getting at a really important point, is that when they first told me about the library navigator, I'm like, why do we have to have another navigator? Because this information is already in the design navigator. You know what I mean? So because I was very much against the library navigator, because I thought, okay, the list is here. It's in the design navigator. Why do I need it again? So they have to maintain them both. So yes, if you add a new cell, like for example, if we look at our cell list here, you can see that here we have cell 1, and in this test file we have cell 1 reference design copy. And these are the top cells, right? So and then these are calling out cells from the design from the library. So yeah, if I went ahead and went in here and did cell new cell 2, you can see it's been added to my library navigator, and it's been added to my design navigator. So does that answer the question?
Yeah, that's my question. So that means
yeah.
We don't need to. So there's no such need to create a library. Whenever a cell is created, actually it's added to a library, right?
Correct. And let me explain the concepts here. Yeah, because you're getting at some pretty good points. That the reason where libraries come from is that they come from other people. So typically, well, there's actually three things going on. The reason why we have a library here in the design kit is, the CMC wanted to give you a bunch of stuff that you did not design. Then for me as a designer, do I need any libraries that I create? Sometimes if I have a project, suppose I am, doing a bunch of I don't know what you do, but I'm just going to say a bunch of biochips. And I know that I am going to, have some repeated parts, like my pad cells or something. I might create a library so that later, when I do different designs, I can then use my own library. And so the only reason why I would need to do that is if I felt like, there's a lot of common stuff that I would use from project to project to project. But if you're one and done and you are, I'm going to design this file, I'm going to fab it once with the CMC, do my PhD and get out of here, then, you don't have to have a library for your own self. Anytime you design a cell, and it can be hierarchical, it's automatically added to your design file. Okay. So that is absolutely true, that you do not have to have a library, and the only thing that you want to do is use the CMC's library to get access to some of these interesting cells. And in fact, if you decided that you don't want to use any of the cells from CMC, you don't have to, because the only thing you need from the design kit is the layers and the design rules and the grids. So if you wanted to, you didn't have to go in here and, set up this library. You did not have to do this. You could have simply brought in the technology from the class, and from the class technology, you could have hand designed all your own pads, all your own JFETs, because you know the design rules and you can create them yourself. So the only reason why we're giving you the library is that, Priya made some really good cells that you may want to use, like these JFET cells. Or if you wanted to be sure that you had a good pad library and a good frame, you can call them, you can get them out of the design kit, but you don't absolutely have to use the design kit as a library. Does that make sense?
Yeah, definitely. Thank you so much.
Yeah, sure, absolutely. And these are all really good concepts to ask about. So please, if anyone else has a question related to that, let me know. And this is part of good design practice, because, I often making a library is an extra step, and you just kind of think about short-term and long-term, because in the IC, world, we often do use libraries because we put commonly used structures into them. And MEMS, we also do the same, that if I'm going to be designing a series of gyroscopes, for example, I will put in different, I'll make a parts library for my gyroscope, because I might have design 1, design 2, design 3, all are different combinations of my gyroscope parts, which I grab out of my library. But, as I said, if you're really thinking that you're just going to do 1 or 2 designs, it's probably not worth it to make a library for yourself. Okay, alrighty, then I think we are done with this topic, unless someone else has a question, which is fine, just go ahead and ask it. While I take some water here. Okay, we are going to then move on to another topic. So I will close my design. So my test 2.3 is not going to be saved. Who knows what I left in there. Okay, so we are now ready to go. We're going to talk about GDS2 and output, because that's the last step of our journey, is that we want to now send our design data either to our friends or to the CMC or to the fab. And we want to be able to make sure that the data is being translated correctly. And as I said, the CMC could extract, oh, not this again. The CMC could extract the GDS out of your LEDit file, but it's good to know, because maybe, you might even want to go to Cadence or something. You want to know how to read and write GDS properly. Okay, so we're going to talk about GDS writing, and we're going to talk about GDS reading, and then we'll do some exercises together about that. Oops, didn't want to do that. Had too many cookies for dessert. Okay. Okay, so the stream in and stream out feature allow you to import and export your mask geometries in standard formats. So there are 2 formats that are commonly used. And as we talked about, GDS2 is a binary file that is used typically in industry for exchanging designs. And there is still some use in universities and small houses that use CIF That's from my old alma mater, and I even spelled their name wrong, Caltech. So as we discussed, the GDS2 file contains no color information, no name information. It does contain the hierarchy of your design, but it also contains no curve information. There's absolutely no curves in GDS2. And Caltech intermediate form does have circles, surprisingly, but nothing else. So you can put a circle into a CIF file, but you cannot put say a torus. And the two formats use numbers in the case of GDS. And in the case of CIF, we use letter codes to map your technology layers. And then it's just basically, each of the layers gets written out and all the polygons on those layers get written out. So it's done on a layer by layer basis with no other information. There's a hierarchy of cells, just like we talked about. And that's why we, when we looked at the cell definition, new cell, we talked about the fact that GDS has some restrictions on the names of the cells, so that you can't put spaces or asterisks in your cell names, and that's because GDS2 does not like them. And, to kind of get at the question someone asked in general, how do I know what those numbers are and where do I get them? Well, typically, if you are not working with a CMC and you're working with a fab directly, the fab has to send you the list, or they send you the design kit. And in this case, the CMC is the sender to you of the design kit, and these GDS numbers are there in the design kit. And so the way it works, for me, I always double check and make sure when I bring in the layers from the design kit that the GDS numbers are there the way I'm expecting, because when you write out the GDS, if it has no number, it does not get written out. Whereas if you read and write your TDB file, if the TDB file doesn't have a GDS number, it will still save your data. It will, if I have a poly, let's take metal, for example, if I have a metal layer in my TDB file and there's no GDS number, when I read back my TDB file and I open it, file open, your metal layer is there. It's just fine. But when you export your GDS, if you do not have a GDS number and you read that GDS back in, your metal is gone. So please be aware of that. So normally you can recover it from your TDB file, but many people have sent to their fabs, a GDS file, and it's missing some of the layers that are needed for fabrication, and then people are unhappy, either the fab or the designer. Okay, so we are going to go into the GDS import and export window. And, and we'll take a look at that. But first, you've seen this a couple of times now, but I'll just remind you that each layer has a setup. And for each layer, we can set the GDS number. We can set what's called the GDS data type. And what the GDS data type is some people use this number to differentiate for the same layer, GDS number, primary number, different purposes for the layer. So I might have GDS number 1 data type 0 and GDS number 1 data type 1, and those are actually different layers. But they're related by their primary GDS number. So I might have metal 1 that I use for the pads and metal 1 that I use for routing, could be data type 0 and 1. Because this process, this JFET process is so simple, we only have a couple of layers, we have them all the same. And one of the things that's interesting is that the original definition of GDS did not have many GDS numbers that were allowed. There were only 64. So you could only have 64 layers. And modern IC processes have like 256 layers. So they had to use the data type to increase the number of layers. So you can see how this data type is used, but for our purposes, It's either, blank, which implies data type 0, or, it's set to 0 explicitly. And then the CIF name can also be set if you are, using a foundry that likes to have CIF. And both of these numbers can be specified at the same time. You can have a GDS number specified for a layer and a CIF name. CIF names are 3 or 4 letter codes, like poly could be CPZ or something like that. But we won't talk about CIF in this class other than what I just mentioned, because we're all going to be based on GDS2. Okay, we talked a little bit about that. The GDS number goes from 1 to 64. Data type is optional. The CIF codes are 3 to 4 letters, and depending upon what you do, you have to make sure you have a GDS2 number. Okay, so now we're going to look at how to export the GDS. So I'm going to go ahead and do this live for you, but these slides are here for you if you then want to practice this on your own. But it's more fun if I just do it directly in the tool. So let's bring up Edit. I have to have a file open in order to do that. So let's see what happens if we export my JFET design. Okay, so if I had a cell open, now I'm going to go to my file, export GDS data. And you notice here I have other choices. I had the GDS and CIF, and we consider those to be mask formats that would normally be sent to a mask vendor. As I mentioned, we can also modify your Tanner database and write it out as something called OASIS. There's also DXF, which is readable by AutoCAD, and Gerber, which is often used in making PCB boards. But the two that are usually acceptable by foundries, like integrated circuit foundries or foundries that make MEMS, are GDS and CIF. So those are the ones we're, kind of focusing on here. So here you can see that the way Edit works is by default, it takes some information from your the file that you have open and the cell you're looking at, and it asks you, you have to fill in a bunch of stuff, which is what I'm going to go over here. So it takes the name of the GDS file by default from the name of your TDB file, but you can of course change that, and you can browse to where it's going to be located. And Edit by default assumes you want to put the GDS file where you have your design file. But as I said, you can browse and you can change that. And the default extension for a GDS file is .gds. And I've never seen a foundry or anybody else that ever changes that, because you always, give me your GDS file, it's .gds. You could, call it something else, but there's absolutely no reason for it. And these GDS files can get pretty big, so Edit could zip the file for you. Our files are so small in this JFET process that we'll just go ahead and send them as a raw GDS file. Now, GDS is a binary format, so it's pretty compact. GDS files tend not to be that big. CIF files, on the other hand, are ASCII text, so you can read them, you can interpret them easily, make a MATLAB program to process them. But GDS format is a proprietary binary format, so you have to know how to read and write it. And there are readers and writers on the web, but Edit will do that for you just fine. Now, the other thing that you want to be sure that you're doing is the correct export scope. Now, GDS does not have a way to tell what is the head of the hierarchy. So even it's hierarchical, but it does not force you to have what we call a top cell. So for example, I could have a file in Eledit that has multiple chips in it, chip 1, chip 2, chip 3. And then when I write GDS out, I would then have, 3 different tops of the hierarchy. So, if I sent that to my mask manufacturer and my fab, they would not know unless I sent them an email which chip that they should fabricate. So you often have to indicate, if you have more than one chip in your design, in your GDS file, you have to indicate which one you want. Whereas SIF forces you to indicate what the cell is that you're going to fabricate. It's called the fabricate cell. But GDS does not have to do that. In fact, you could exchange in, like the library that we have, we can have a GDS library where there's no chip in there. There's just a bunch of cells. And so that's why when we have this export scope, we have to be careful about how we think about what we want to export. So typically we could export all the cells if we know that, which one is clearly the hierarchy. We can export the active cell, which is the one that we are currently designing on, the one that's in the being highlighted with the darker bar on it. We can export the fabrication cell, and I'll show you that. We can mark a cell and say, this is the root of the hierarchy. This is my cell that I want fabricated. We can choose a cell here. Like, for example, I had this my bad copy JFET design. So it by default grabbed that as because I had it, that was my cell that I had open. And then you can browse the cell list from the library to choose which one you want to export. You can export a bunch of cells from a library if you want to share them. You can also select them in the design navigator. I don't know if you noticed in the design navigator, there's some checkboxes that can occur that you can choose which ones you want. And you can either include all the little cells beneath them or not, just include the cells that you have, the hierarchical level that you have. And you can also exclude the library cells. So if you don't want to export any of the libraries in there, you don't have to. So there's a lot of choices here. So basically, we always give a recommendation. I either choose this one, which is the cell that I'm working on right now. I go in there and I say, before I do my GDS out, I put that cell right there. I know this is what I want to output. And then I go to File, export mass data. I choose that cell and write it out, because then I know exactly what I'm doing. Or I don't care and I just say I'm going to export all cells, because I know that I have a main top cell, and it's pretty obvious to whoever's pulling up my design, what I want to do. Okay. Then when we write the GDS out, it's going to automatically pop up a log, and you can save that log file. Typically, I don't bother, because it'll pop up the log and you can look at the log, and then you can decide to save it then. Like, I let it open the log in a window. And here in Eledit, I'll show you this later, Eledit has a little command window. It's kind of a place where you can edit, you can enter commands for Eledit. So it can go, you can put the log into the command window, because it's kind of like a little, it's recording the things that you do, or it can record the things you do. So you can put it in there. But I usually just like to put it into a window that I can see. So that's kind of the left-hand side. Now on the right-hand side, we have some additional options. So let's go over those. Now, the default database unit in GDS is 0.001 microns. So that's a nanometer. And so there we are, that's what, GDS would do. But we can also create a custom unit based on an element fills this in from the database, the technology units that you set up. So you'll see this number is auto-filled. So typically I leave it at custom because, you know, if I want to have this GDS and I'm going to read and write it, I want to have it correlate to how I set my grid and my resolution in edit. And so custom is the default in this dialog. And then I want to preserve the case. Some old GDS readers can only handle uppercase cell names. Some can only handle lowercase cell names. And in this case, I'm going to preserve the case of the cell names that we have. And again, you know, this can happen in university fabs or smaller mask shops or whatnot. You know, you may occasionally, you know, come into to some reason why, you know, uppercase is all you can do. And then we also can restrict the cell names to a certain number of characters because all of the cell names, you know, in the original definition of GDS2 could only be 32 characters. Now, we have some customers where they have cell names that are like 100 micron, that they're 100 characters long because they have my pad cell underscore this, underscore that, underscore the other thing. So, you know, be careful here because if you choose that restricted 32 and your cell names are really long, you're going to have a problem because some of your cell names could get truncated or, you know, or some of the cells could be missed because they are the, you know, they are set according to something that you weren't expecting, right? And then so be careful about that as well. I think in this design kit, the names are pretty short, right, Priya? Nothing,
Yes.
Nothing close to 32 that I remember. But anyway, you can change that. Virtuoso, which is cadence, has a standard of 128, or you can have unlimited. You know, no harm in choosing unlimited unless your vendor has a limit of 32. Okay, so then we have what's called a mapping file. And that is, I think that's a question that we had yesterday is how, you know, what happens if I'm going to a different fab? And I labeled my GDS layers 1, 2, 3, 4, 5, and you know, there's our 37, 24, whatever. You can browse to a file, it's called a map file, that will map the layer names that you're going to export into some other GDS numbers if they are, you know, if they're there. And then we can also specify a couple of other things that we're not going to export hidden objects and layers, which is really helpful because sometimes we may be, you know, designing some things like that we have, you know, put in there for reference, or, you know, we just don't want to export those objects. So in edit, we can hide them and then not export them. And same thing with layers. This can happen, for example, suppose our fab, we made a mistake and we screwed up, you know, the layer that's called metal, but all the other layers are fine. And the fab says, please resend the metal layer. Well, I can hide all the layers except metal and export my GDS file again, and they'll just get the metal layer. So there's reasons that you would want to do this. And so, yeah. Then there's some other options that we probably won't go into here in this class, this object data type and layer data type, that's kind of an advanced thing. Moses, this is a legacy option. In the old days, there was a maybe people still use it. Moses was a fabricator of IC designs, and they required that every GDS file had a checksum, so they could be sure that they were getting the proper, you know, the internet was actually unreliable. So whenever they would get a file, it might not have transmitted correctly. So we had to compute checksums. And then the other thing that I always do is I always check this one, which is self-intersecting polygons and wires. And when we talk about good design practices, I will go ahead and demonstrate what a self-intersecting polygon looks like. And then the other thing that we talked about is that, you know, if your mask maker cannot handle more than 200 vertices in a polygon, Edit will fracture the polygons before it writes them out. So is there anything that I haven't on this, you know, screen that I haven't explained well or you're wondering about? Nope, pretty straightforward, much easier to understand than libraries probably. So at that point, once you have very carefully gone over your all your options and everything like that, then you can just hit export. So we'll do that. And up pops the log. So there's a lot of interesting information in the log. It just basically repeats back to you all the options that you have chosen. And it's a good thing to just check, you know, about, you know, you can see here that there's been some changes, that there's some illegal characters here in this, in this GDS data. In this change, so you can see that it was modified, DRC_rule_1.1. That cell name was modified to DRC_rule blah blah blah, because there is, you know, you're not supposed to put a dot. It's an illegal character in the cell name, and you know, so that's okay, because in this case, these are just the files that are, these are just the little DRC rule cells. So we don't really care about them, but good to know, good to check the, this information. So Priya, you should make a note of that and change the design kit to get rid of those little points.
Sure.
Okay. But no harm, no foul on this, because this is not impacting our actual data. And then you can see here, it's telling you, for example, cell 1 is empty. That's right, because I didn't put anything into cell 1. Remember, I just did a new cell there just to show what happens if we have a new cell. And then, you know, there's other you know, things like grid layer has no objects on it, just telling you that that's empty. And then someone drew some icons on the icon layer, and that doesn't have a GDS2 layer. So so this just is telling you that as well. So we have some things we can clean up in the design in the PDK. And but none of the design data would have been written out incorrectly. So always good to check your log file. And then you can just save it if you want. Okay, so any questions about writing out your GDS?
Thank you, Marianne, for explanation. Now I have a question. I don't know how to describe it.
Sure.
For example, I have my design chip, and I have some, for example, I want to coat it with polymer later. So I want to cover some areas. I was wondering if I can get any like output from Edit, or I don't know, maybe from like GDS, that, you know, it gives me the areas I want to cover.
Sure.
And I can export that that's like output to, for example, AutoCAD or other softwares.
Yes, absolutely. You can actually output that to, you can export right there to DXF, and AutoCAD can read that DXF for sure.
But I don't know how I can explain. For example, in polymorphs structures, they have some releasing holes on top, right?
Yes.
I want to cover those holes.
Yeah.
And then, for example, a spray polymer.
Yep.
So I am looking for a file that I can, cover the specific areas I want and then coat it.
Yes. Okay. Yeah. So you could do that. Okay. And let me explain what you would do. Okay.
Thank you.
All right. So let's do this. Okay. So what you're going to want to do is that you have the design kit from the CMC, and then you would maybe, for example, add a new layer. You would go to set up layers, and you would go ahead and add, a layer here, and you're going to call that cover layer. And again, tell me if I'm not doing what you want. Cover layer. And so you now have a new layer called cover layer, and we'll say that that's let's find some nice purple. I don't know if we're using purple. I think we're not. So now you have a new layer, and you can go in and you can go ahead and make a square, and suppose you want to cover this area. I'm just making this up, okay? So now you have not assigned a GDS number. So this is not going to be a problem for your design, because you have, there's no GDS number, but we can write this out in DXF so that, DXF AutoCAD can see it and things like that. So if you can even give it a GDS number that's different from the ones that are going to be used with the fab for the 3IT and CMC. So you can add additional layers to LEdit that go above the layers that are used from the design kit. That's not a problem, because when you read and write your TDB, you will bring in the design kit layers, and you can always merge them with your layers. Okay, so you can add layers to your design, and you can, it's kind of outside of what we talked about in the simple class, but there's ways to manage that, so that you will be able to have your layers on top of the layers that come from the CMC. And is that what you wanted to do? You wanted to have some additional regions that you use for your own purposes, is that correct?
Yes, actually, I want to cover some particular areas. For example, those holes, I want to cover them and then do spraying.
Yes, understood.
Thank you.
Yeah, and there's other things you can do too. It doesn't have to be a design layer. There are other layers that LEdit has hanging around that you could use for, and this is something that we may want to talk about with the CMC, is that, a lot of times researchers will take a process like polymumps or even this JFET process, but you need to add some features because of what you're going to do with it, right? So, maybe that should be part of what we teach, is that, here's the design kit for fabbing this part of your design. And then if we're going to do printing or who knows what, maybe you need to specify some additional layers that you're using for your own purpose. And that's what it sounds like you're doing, right?
All right, thank you.
Sure, no problem. All right. And so we'll follow up with you and give you more of an explanation of how to do that, because it's going through that right now is a little bit beyond the scope of what we're doing, but I just wanted to kind of give you an idea of how it might be done. Okay, and we can follow up with you specifically of an example, for example, is it polymumps that you want to modify?
I don't want to modify actually the polymumps itself. I want to, when the chip is fabricated.
Yeah, you want to do it afterwards, right?
Yes, afterwards, exactly.
Okay. But my point is, you're going to take a polymumps chip as opposed to this JFET process.
Right.
Okay. All right. Well, follow up with Priya. Just send her a quick email and say, hey, can I have an example of how to modify a process to add my own layer? Because we do cover that. And maybe in the fall, you can take that part of the class where we talk about creating your own technology. Okay.
Okay. Perfect. Thank you very much.
Yeah. No. Sure. No worries. Okay. So, any other questions about exporting data? Because now we're going to talk about importing data, and that's actually there's more to it. But export is relatively straightforward. Now we will, we kind of went through these notes, and you have these notes. I went through it with you specifically, and now we are going to go through the GDS read-in process, and if there's no questions about the GDS writing process. Were there any other questions? Yeah.
No, we're about 1 hour 40 minutes from closing for today, so we would could we finish this in next 15 minutes? So we take a 5-minute break and wrap up the last section.
Absolutely, absolutely. Let me see what we were going to talk about. Yes, what I can do, Priya, is I will just finish this, and then we will I'll go ahead and cut short the exercise, because they can do that on their own. So I'll just do a quick demo. Okay, sweet. Okay, so now we'll talk about GDS read-in. So similar to the export dialog, I am going to go ahead and do this live, and then I'll do a real quick example so that we can get to some of the things that Priya would like us to talk about. Okay, so we are now going to go into import mask data, GDS2. So here we're going to be bringing in a GDS file, and you can see here that if I have multiple designs open, it's asking me where do I want to bring this GDS file into. And you notice that it's not allowing me to read a GDS file into, even though I have a library that is, from the design kit, I'm not allowed to change that library. So I can only bring in GDS into one of my designs, okay? And then one of the things that's important that I do want to go through is that if when we read in the GDS, we want to do that once we have set up the technology, because what's happening is the GDS only knows the numbers that are in the GDS file. So in order to map them into the layers in LEdit, we have to have set up the technology, because otherwise, if we have a blank file with no technology, we're going to have unknown layers. And so LEdit can bring in a GDS file if you have one into a file that has no text setup or no file setup, but it's going to have to either generate new layers or prompt you for what should I do with these layers. And I'm going to show you that real quick, because Priya wants to make sure we covered the other stuff. So that's important to know that you want to set up your technology so that when the GDS file is read, that the layers can be found. So, if you're going to bring in a GDS file, don't bring in the GDS file and set the technology. It's better to set the technology first, and then the GDS file will match it. The other thing to notice here is this overwrite cells in the target library. If you have a design already, maybe you got a GDS file from somebody, or you have your design, and now you're reading in a GDS file. What happens if you already have cells by the same name in that target library? So you can either overwrite them or not. And this happens, I was working with Cotter, Priya's colleague there, is that he had read in a GDS file and he had his file, and then someone sent him a new GDS file that had the same cells, but the geometry had changed. It was like an update. So he had to make sure to check this box because he wanted to overwrite the cells that he had in the library with the new ones coming in GDS. And if you don't check that box, LEdit will just say, well, I already have a cell by that name, I'm going to ignore you. So make sure you understand when you're reading in a GDS file, whether if it's replacing the data that you have or it's new data. Okay, and then also here, this is an option where we can treat the different data types on a layer as different layers. As we talked about, we can have a GDS data type, so we can either merge those data types, or we can create different layers from them. And then again, we can read the resolution of the database from the import file, or we can set a custom resolution. So what will happen is if we read in from the imported file of 0.001, but in Tanner, we've set our database resolution to 0.01, we're going to just truncate that the numbers coming in from GDS. But if the opposite is true, that the GDS file has a resolution of 0.01 and we have a database resolution of 0.001, then then LEdit will just simply, you know, add another 0 on and give those polygons an extra resolution, you know, an extra degree of resolution. So just be careful and make sure you understand the database resolution of what's coming in, and also your database resolution that you set in LEdit. And then there is a log that we're going to open in a new window if we want, or we can put the log to the command window. So I'm going to do a demo very quickly, and so before the break, of reading in a GDS file, and we will read it in two ways. We will read it in with outsetting the technology so you can see what happens, and then we will also read it in with the technology present, and we will see, you know, how that goes. And if we have time, we will also show you how to replace, you know, if we modify the GDS. And if we don't have time, there are some exercises on this that we will, you know, you can do. Okay, so let me close this up. Don't want to save it. Okay. So what would happen if we imported some GDS that we had just written out, right? So let's go find the GDS that we wrote out. I think it was in the training. Let's, yeah. So this is the GDS that we wrote out when we did the output step. So let's go ahead and read that back in. And we will generate new layers if we don't know them. So we'll just go ahead and import. And now we have the log file, and it said, hey, it found all these unknown layers. What am I supposed to do with that, right? So here is, you know, the log. So it said it created them. And if I hadn't set the technology, it's going to create layers because it only knows the number. So LEdit will create a layer, and the layer name is going to be GDS underscore the GDS number, DT for data type, and the number that the number of the data type. So it's telling me that it's a warning. It does have everything there in the log, and it did read it. But now if we do cell open, let's go look at, you know, our stuff. You'll see here that it has read in the GDS data about the JFET, but it doesn't know any of the colors. It doesn't know anything, you know, it just created them for us. So if we go into setup layers, instead of our layers being, you know, implant, metal, blah, 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 it's just called them GDS underscore, you know, blah, blah, blah. So if you want to bring in your GDS file, you have to set the technology first. So let's go ahead and do that. I think I can do that quickly. Okay, so let's do this. Let's do new design. And all right, what the heck? Let's make test 24. So now we're going to call up the design kit. We're going to use a technology file from the design kit. And now we are going to do our import of our GDS. same GDS file, and we'll let it generate new layers if it needs to. And now if we import, you will notice that there's no complaining about layers that it doesn't know. All right, it knows there's no zero, there's no warnings, nothing going on there. And now if we look at, you know, my bad design, let's see if we can find it there. Now it looks like what we're expecting. So we can read and write the GDS, but we need to make sure that if we want to use the same colors and names of layers and things like that, that we attach to the technology first. And then we read in the GDS, and then we will have all the information that we're expecting read out of the GDS file correctly. So what happened because we didn't set up the tech file, Edit just did the best it could, and it created the geometry with names that were that it created on its own, which is not what we want. Okay.
Okay, hi everyone again. I know we talked a lot about this. The slide that I'm showing right now is just so that I have some continuity here. So as we discussed, the electronic sensor platform gives you this ability to develop your functional material of your choice, and that has led to many other applications. So the first application for which this platform was developed was for optical or photo detection using colloidal quantum dots. That was used as the functional material, and this application was successfully demonstrated and has in fact generated a Nature publication. And since then, this platform has diversified into several other applications, especially in the field of biosensing. You can see here ambient sensor, radiation sensor. So currently we are working with two groups. One of them is trying to deposit graphene as the functional material and then using it for various other detections, like as a gas sensor or insulin sensor and pH detection. So the other group with whom you spoke in the morning, Abbas, today, so what they are trying to do is use neutrophil detection for COVID-19 analysis. So there are a lot of applications that this platform can offer, and it's currently limited by our imagination, and we hope to expand what it could do with your support. So I'm going to show here some of our previous designs.
Oh, Priya, you cut out for a minute there. Can you re-say the last, just this last bit, introduction to this slide?
Okay. So I'm just now showing you some of our previous designs. So just to give you an idea that the layout may not be like the reference design layout that we did. So what you can see on my screen right now are two of our previous designs. So on the left-hand side, this is our first design that was there. At the center, you can see there are like about 5 to 6 devices, and all of these are actually pads. So they wanted huge pads to make connection. So this was actually a 10 by 10 chip, and they have only used about 5 to 6 devices on the entire design. So, and on the right-hand side, I don't really know what application this spun out to, but I think this was something to do with depositing organic materials. So the person tried to make a contact to the gate and laid his devices like this. So there are 2 more designs that we have. On the left-hand side, this is again a 10 by 10 design. This was specifically done for microfluidic applications. I don't know if it's clear to you, but what you can see here is they have only one common source and multiple drain pads. So they have done a multiplexing here. This is one option that you could do too. On the right-hand side, we have another design, which was done for graphene printing that I was talking about. So Miriam, would this be the point where we would talk about some of the things that we need to consider when we are designing the layout?
Yeah. Let's talk about this because you know, in fact, this particular design, we can. So if you look at the design on the right-hand side, when we talked to this student, we discussed with her that one of the issues for doing biological chips is that you often, any place you have a pad, you're going to have an opening in some way, right? So one of the things you might want to consider if you are doing some sort of biochip or any kind of deposition of material is to make sure that you have enough space to do so for that particular either material or whatever you want to do. So that is one reason why, the frame cells that are coming from the CMC have the pads around the periphery. And you may choose to only have pads on, like, say, the left-hand side and the bottom, and maybe leave room so that whatever biology or things you have to deposit or whatever you want to do has room on your chip. Because one of the issues that we observed when we were talking to students was, handling these chips and testing them and then putting stuff on them or applying making sure that whatever they did put on there didn't contaminate or short the other devices. So if you are going to not do much to your chip, then you might be fine. But one of the things that you may think about is leaving a big space in the middle if you're going to deposit something, or having a strategy before you start laying out your chip for how the whole system is going to fit together, how you're going to mount it for testing, and also getting access to the pads. Because one of the issues, if you see the design on the left, this person has really big pads, and they probably have that for a reason, right? So Priya, do you know, the pads that the pads that are in the design kit are only 80 by 80 micron opening, which is probably okay for wire bonding, but there may be some other type of connections that you want to make. So a couple of takeaways on best practices. One, think before you start laying out your pads. Think about the structure of how you're going to access your pads, making sure they're big enough for the kinds of connections you're going to do, whether it's probing or something else. And then also think about the biology and any sort of spread of the device, the material that you're going to put on top, and how you're going to, the one person was dispensing some material, and it was pretty blobby. And so they wanted, they had some problems with these pads being, not around the periphery. And even more, it would have been better for them to have them only on two sides so that they could bring in their material from, say, the upper right, and not have any collisions with either the wire bonds or the openings in in their wires. Because you can see here, like if you were going to put something on top of the gates on these devices, right, the via gates, you will also, be putting that material most likely on some of those pad openings, where if you have all your pads on the extreme left and the bottom, you can come in, dispense something onto the top of your gates, and those other probe pads will not have so much of a problem. Or you could even cover them in some protective material, while you're doing the dispense. But if you have those pads in the center, you're kind of asking for trouble. So is that what we wanted to kind of convey, Priya?
Yes.
Right. And then the other thing with the design on the left is that we're not too sure yet that we have a good model if you have a common source. So one of the things that you may want to do, even though it's kind of nice for routing and it's also efficient, you might want to be able to control your source and drains, separately, and maybe not do a common source configuration. So I think there's a lot more modeling that's going to happen, of these devices as we go with time. So, maybe being able to control as much as possible maybe a good thing for you. And so that's something that's important. Okay. Did you, you're going to move on to your design as well, Priya?
Yes, I will. Just a couple of more things here.
Yep.
On the right-hand side, you can see there are some test structures. This is the TLM structure. You'd see that in the reference design too. So these are developed just for you to test on your end for any sanity check or things like that. And also because you would be looking under the microscope or in a probe station, we recommend that you give some indication, like could be a number or a mark or something, so that you know where you are if you have so many multiple devices on your chip. So that's one good thing too.
Right, and as Priya mentioned, probably a good idea when we talked about the text generator to use letters and things like that that are fairly orthogonal and aren't too fancy, so that you don't have any little pieces of your either your logo or your numbers floating off into space. And we can recommend some good text generators if you if you want to do that numbering as well.
Yes, and always think of how we are going to access these these paths. Like think of the final packaging before completing the design. This was now this person doesn't think they want to do wire bonding, they want to try with pogo pins, but then these paths are too small to do that. But then initially this was done to have more devices on the chip. So there's a trade-off with how much you can do compact packaging, but then like think of the end, how you are going to access all these paths. Similarly, for this design, I think they want to use pogo pin, and they have a microfluidic interface. So they have developed an integration board with that. So think of the end application in mind, and then go about designing it. So from CMC side, we also have another reference design. It's not yet part of the layout, but this was done for specifically for a fluidic interface. So on this, what we have done is we have put all the parts on one side and then given cut, and the JFETs are here, so that when we design a microfluidic channel, these are not interfere. The pads do not interfere with that. And we are also developing a microfluidic package for that. Mm-hmm. And this is a 10 by 10 layout. And now coming to the reference design that I have developed. So this was done in a more generic way to give more options to users with different channel, again, in the conventional sense, channel lengths, or here what we call them as the gate widths. So one thing that is available to you as users, you could we would make this available to you off the shelf. So if you want to take one of our reference design and then actually deposit your material and see the characteristics, you could do that. That way, it would help you in designing what you want to do. Like if you want to do that first check whether I want to go with this kind of gate length or gate width, so you could do one check with that. Sorry, were you saying something, Marianne?
Nope, I'm good.
So we also tested these devices at 3IT but there was no material deposited on the top. So these are the transistor characteristics that we have for our reference design, which will act as your base point for you to compare once you deposit your own material.
So Priya, so I'm sure these DD were these for the reference design that's shown on the right there? Now go back one slide.
Yes.
Is that for this design? So how did you connect? Did you end up jumpering the gates? How did you connect the gates? Because your pads don't connect.
So this was done with open gate. We did not make a gate connection.
Ah, okay. So there are connections to source and drain. There's just an open gate. And then what's the variable being swept in the plots?
Just the IDVD. We have not applied any gate voltage.
Okay,
sorry.
So VGS is a back gate or what?
Back gate, yes. The top gate is left open.
The top gate is left open and the back gate is swept.
Yes, because the top gate here has not been connected with any material, or we've not deposited anything. So we have taken the connection from the back gate.
Got it. Okay. But the source and drains are connected.
Yes.
Oh, the question is, where is the pad to the bottom gate? So Mohammed, there's a giant, that material, gate material is deposited everywhere, I believe. The metal is everywhere, correct, Priya?
Yes.
Right. If you go back to the fabrication process, can you, maybe that was your first slide?
Yeah.
See the bottom gate there, Mohammed, it's everywhere.
So if you were to do on the probe station, it would be the chuck connecting to the entire thing.
Right, exactly. Yeah, hopefully that answers the question. Okay, thanks, Priya. I was just wondered about that. And then shall we look at your design in Edit to see the hierarchy that you used? Or do you have more to say about these slides?
Just
Oh yeah, go ahead. Yeah, go ahead.
last few things, like for somebody who wants to design and prototype for this technology. So in the PDK, as Marianne has already spoken to you about, we have the Edit kit, the user guide that comes along with that. So we also have information on the first application of quantum dots that we have. So we have models from that. So we have Centaurus models which were developed specifically for that application. So it would come in the same package. And we are also integrating the COMSOL models that Abbas spoke about in the morning. You will have access to that too. So the typical design flow would be, I don't see here because of this. Okay, you would design your layout in the Edit, and then it goes to fabrication at 3IT. This process takes about 3 to 4 months. So when that material comes back to you, you can integrate the top functional material and then test your devices. So for you to get on the upcoming run, to book your seat on that, you have an application deadline of 18th. So by then you just need to indicate that you want to be part of that run. And then we'll work along with you to help you with building your layout, understanding your application, and thinking about the packaging aspects. And then that layout goes to lab by August 20th. And you could expect the chips to be delivered back to you by December 20th for you to start your testing.
Nice.
So yes, and this is at a huge subsidy right now that is going on. So you could actually book your run only at $100. So that's as much as you paid for the training or less than that. And just again, to reiterate, if you were to design a 10 mm by 10 mm chip, you would be getting about 10 to 11 chips. And if you were to design a 5 mm by 5 mm, you would multiply approximately by 4 and get about 44 to 50 of those.
All right, so let me, can you guys see my screen?
Yes.
Okay, great. So let me open the design navigator. And we'll talk about Priya's design. And we'll see what's in there. Okay. So you want the one that is reference design, right? This one. Okay. Okay, so if we look at the reference design 5x5, it's using 108 pads that are 100 microns, 8 pads that are 10 microns, and 4 pads that are 40 microns. So she's calling out from the library a bunch of the pad cells. So that's one thing that she does is she's not designing her own pads. She's going ahead and using them from the library. And the other thing to note is that then she has created here this reference design, these reference design cells. Let me see if I can, my mouse is a little funny. So these are the she created this from individual instances of the auto-generated JFETs. So what she's done is she's created her design hierarchically so that she has her frame that goes around the outside. She has her pads that are coming from the pad library, and she put them down in a regular fashion. And then, as we discussed, it's always a good idea to create a core of your design with your different JFETs. So for her design, for example, she chose to, as she told you, she used a JFET generator and a gate generator because she is sharing sources and drains along a line for her device. But the idea, though, is she has all of this stuff, which is her active area, into these reference design cells. So here, these little blocks are blocks that she can move around on her floor plan of her, entire device. And so she can easily move them or edit them. She can edit them here in this cell. And then since she happened to repeat them, they will, she will be able to easily manipulate them. So her design has a lot of hierarchy. And then, correct me if I'm wrong, Priya, but at the end of it, you then did routing at the top level where you just took, you knew you need to have to connect these pads to the sources and drains, right? And if you look at how she did that, she's got, she has those connections coming out orthogonally, and then she jumps into an all angle route. And as I said, she could have chosen to do, a 90-degree route. She has the room, but it's also easy, might be easy to even grab a wire to do her wiring. But the important thing is that she made good use of hierarchy, that she had her pads, that she put down in her frame, and she had these core cells that she designed so that she could go ahead and group them together so that she could easily move around and the blocks of the designs and line them up with her pad. Whereas if she had, designed the JFETs in the same cell with her pads, then, it would have been hard if she wanted to change something. She might have had to move a whole bunch of stuff out of the way. So do you have any other comments on the thought process behind your design style there?
No, the only thing I did this kind of multiplexing is just so that, because it would give more option to users, because I was not sure whether somebody wanted the 5 micron or the 10 micron. So I have used a common source which could act like the drain too. But then if you want to design, I would suggest, separating that out, because just in case, let's say you burn off one of the devices, you would not be losing 2 of them. So
exactly. So as we talked about, is in maybe your first designs, you don't want to try to share drains and source, and you don't want to have a common source if you can avoid that. And in her case, she was this is kind of like a test chip. So she had some pads here in the center. But for you, we would recommend thinking about, what you're going to do in terms of the material you're going to deposit so that you don't short out anything. But the nice thing is that, as I said, her design is very hierarchical, and that will aid you in being able to quickly modify the design. And you can see here, she's used her JFET cell 3 times and her gate cell twice. And then she just gave it different parameters there are some that are, wider than others. And she was quickly able to do that by just regenerating the basic cell with different inputs. So hopefully you'll be able to do something like that as well. And then the other thing to note is if you do put on a logo, she has chosen to put her logo in a cell. So she has the CMC logo is in a cell. And that's very important because when you go to DRC, you want to temporarily delete that cell. because she's going to get all kinds of trouble because she's violated all kinds of spacing rules probably in the logo, but but that's okay. It's a logo, right? So you want to take that off when you're design rule checking the main part of the design. But for sure, make sure if you do a logo that it's not going to hurt, any of the fabrication, because, you don't want to, you don't want anything that is going to break off or affect someone else's chip, right? So, please take care when you're having your logo, but it doesn't have to follow, your logo is not going to follow the design rules, right, of the JFETs. So put it in a separate cell. And as Priya mentioned, she's got different markers there. So when she looks at it under the microscope, she's going to be able to see what is what. So I think there was a question about how you make these design kits. Is that right? Was that person still interested in discussing kind of the history of the design kit and what we're likely going to do?
Yes.
Okay. All right. So I'll give a little bit of background, and Priya, you should probably jump in because you know what happened with the actual technology, right? So when, first the fab has to decide the fabrication process sequence, right? So they're looking at how the devices are created. So before the design kit happens, they have to figure out what process steps they want to do, and then what masks they want to use when they're creating, their devices. And then, they have a set of masks that they actually use for fabrication, but then we have to think about what are the masks that the designers want to use, right? So as you notice, we did not include the alignment marks in the PDK because those are, 3IT does those. So the first thing is the fabrication sequence, and then they talk to the CMC or who's ever making the design kit about what layers have to be specified. And then, usually the PDK designer decides on the colors based on the number of, the number of layers. And also we try to have some sort of, funny thought about, what makes sense. Like I like to have, my metal looks metal, right? So for example, I might have, my metal be, gold or something like that, or, it can be arbitrary, but you want to choose good colors that are highly differentiated. So the person doing the layout doesn't necessarily have a confusion as to what layer is what. But the fab normally doesn't care too much what colors are picked because they're not looking at that so much. So it's usually the PDK designer that picks that information. And then, then a conversation has to happen with who's the mask maker and what is the manufacturing grid that needs to get specified, right? So that's an important discussion. And then the fab is the one who owns the design rules, right? The fab told the CMC what those design rules were and how they had to be obeyed, because those are all based on fabrication constraints. And typically, like, for example, for the metals, that's a limitation on how closely the 3IT can put those metal lines and how thick they can make them. So the DRC rules are normally communicated to the CMC. And you guys, if I'm not surprised, I would not be surprised if it just came in a Word document. Is that correct?
Yes.
Yeah. So, rather than you having to type all that stuff into edit each time, that's what the PDK is for, is to get that information clear. And I think you can tell there were quite a few iterations here between the 3IT and the CMC, because I believe, maybe you can comment on the story about why there is via gate and via pad, Priya.
Oh, yes. So in fact, the ones that you saw, like everything was blue, right? So that's the difference. So everything was under the layer of via pad. Just in this iteration, there is a lot of confusion as to, the opening for the gate. So we created this layer now, but it's all work in progress, right? So as we get input from the and feedback from the users, we try to modify and make the PDK better and better going forward. So you'll see a lot of revisions. Yeah.
Right. So this thing that a comment that can be made is that in the beginning, when you look at that fabrication process sequence, there's actually a single step where both the vias that go to the gates and the vias that go to the pads, the probing pads, are actually done at the same time. So the CMC could have said, okay, well, the way that we know, a gate, is different than a pad, right? So we have to have some sort of marking layer to describe gates. So if they did want to have, a single GDS layer that specifies the via openings, that is possible, but then you have to have some sort of way of differentiating the rules for when I am creating a via that's going over a pad, say when via crosses metal or something, versus when vias are not on top of metal. So that can be confusing. So probably the easier thing to do is say, hey, I'm making a gate, so I use via gate. Hey, I'm making an opening for a pad, so I use via pad. So it's really the 3IT is using a single mask layer that they got by combining via gate and via pad. So that's why when the question was asked about, what's the difference between the masks that get printed and the masks that we draw, is that the 3IT is probably taking those two GDS layers, combining them onto a single mask, and then using that. So, one of the things that we'll do is to make this more clear is we will, make a little diagram that explains, this is what you draw. This is the tone of what you draw. This is what happens at 3IT. This is a kind of resist. And then you can kind of see the chain. But for you as a designer to kind of do your job, you just need to know that when you're doing the via gate, you follow these rules and you use this layer. But the 3IT doesn't care. They're just, okay, this is my GDS layer that I combined the two, and there you go.
I just have some information on the pricing. So yeah, I just looked that up, and then so researchers can get a discounted price if they were to apply for a resource competition. So that would be peer reviewed. So they would be judged against certain effectiveness criteria that we have on our website listed. So if they want to avoid that, they could skip that and directly go to the other pricing that was shown there.
Right, that's what I thought, that there's a competition, a peer-reviewed competition, and if you pass that, you get the $100, right?
Yes,
that's right. If you don't, you can still go directly on the run with the $3,000 price, right?
Yes.
Gotcha. Okay. Any questions, or do people want to see how to send something to console? Okay, I think we can do it quickly. I'm going to, Priya, did anyone have any other questions? I didn't see the chat.
Nothing on the chat.
Okay, all right, so I'll just run through this briefly. And this is an example that we had from our advanced class, and we can make an example for the JFET as well. But I'll show you the principle of it, and then, since we have the 3D model, we can just send it off to replace the slides that I'm showing you with actually pictures of the JFET. So basically, if you have a layout, which is what's shown here, in this case, I'll put this on slideshow, I guess. If you had a layout, to pretend that what's in the middle, in the right-hand side, is a layout from, of your JFET or your info. We have in MEMS Pro what's called a process definition. And that is a description of the fabrication process. So what we would do is you would take your JFET layout and you would import the fabrication process information that represents how the JFET is made. So we have commands that, you know, describe the implant, the creation of the gates, the vias, whatnot. So you would import that into MEMS-Pro, and then you'll see that the little, you know, the fabrication description will show up. And in the case of the JFET, it will look like, you know, the process steps that I showed you in cross-section. So then you would generate a three-dimensional model in MEMS-Pro. So the tool that you've been, you know, seeing, today and yesterday is actually MEMS-Pro. So you have the 3D modeling capability in the tools that you've downloaded. We just didn't show it to you today. So you will be running the 3D model, and that will generate a 3D model in MEMS-Pro of your JFET or your little snippet. Could be multiple JFETs, but I'm assuming you just want to simulate one of them. And then you would export that because it's going to go into COMSOL. And with COMSOL, we export into a format called SAT, S-A-T. So you would, you know, once your 3D model's on the screen and it looks like what you want, you would export that to SAT. And now you just pop up COMSOL, and you would say, I would like a new model. So you would click on blank model. And now you do add component, and you would say, I would like to add a 3D component, because we're going to bring in a three-dimensional model. And then you can change the name of the component to whatever you called it in the layout. And that will add your component to the COMSOL tree. And now we're going to just import that SAT file that we wrote out from MEMS-Pro. So under the geometry tab, you just click on import and export, and then you'll get a little import there. And you click on the geometry button because that's what you want to bring in. And then the important thing that you want to do is COMSOL thinks about things typically in millimeters. So one of the things that we want to do is make sure that we do an import tolerance of, 10 to minus one tenth of a micron. You could probably even get away with a micron for these JFETs because, you're not going to have much that's below 5 microns. But you want to make sure that COMSOL knows that something's coming in microns. So see this absolute tolerance thing here? Make sure you change that to, because otherwise COMSOL will think that your tolerance is going to be a millimeter by default, and it will then truncate some of your data. It'll still read in, but you'll get errors. And then you click on browse, and you browse to the file that you wrote out, and you click on import, and then your model comes in. So your model will then be displayed in COMSOL for you. And it will then, when it's in COMSOL, the different materials that you made your JFET in will be different materials in COMSOL. So the gate material, the metal material will be different than the silicon material, will be different than the implanted material, and so on and so forth. So you will see different materials in COMSOL, which then you can add your material properties to and whatnot. And if there's interest, we would be happy to go ahead and send some examples. We can redo this presentation with a JFET example if that helps, because it's the same exact process here. We were doing this for a MEMS device. It's the same exact process if you're doing it for a JFET device. So does that kind of give you a feeling for it? We go from an L-edit layout, which is a 2D thing, into a 3D thing, which is the stack of materials, and then we output that and then import it into COMSOL. So does that help you kind of get the idea? Yeah, we'll send this, we will put this presentation and the data file in the notes in the Dropbox, and then we'll go ahead and make a little example, and we'll let you know that when it's ready. This example here using the MEMS device we can put in immediately. The other one, give us a little bit of time and we'll get it up there. All right, bye-bye everyone.
Thank you all.